Long before humanity understood the mechanics of the cosmos, before telescopes pierced the veil of night or spacecraft ventured beyond our atmosphere, people gathered beneath open skies and watched in wonder as streaks of light traced fleeting paths across the darkness. These luminous visitors, appearing without warning and vanishing just as quickly, became woven into the fabric of human storytelling, spirituality, and imagination. The ancient Greeks called them meteoros, meaning high in the air, a term that would eventually give us the word we use today. Across every culture and every continent, falling stars have inspired myths of divine messengers, omens of change, and windows into realms beyond our earthly existence. Tonight, we embark together on a gentle, unhurried exploration of these celestial wanderers. We will trace their origins from the earliest moments of our solar system's formation, follow their long journeys through the emptiness of space, and witness the spectacular transformation that occurs when they finally encounter our atmosphere. We will visit ancient civilizations who revered these objects as sacred gifts from the heavens, and we will explore the cutting-edge science that allows modern researchers to read the stories encoded within meteorite fragments. Along the way, we will pause to appreciate the profound connections between these cosmic travelers and the very existence of life on our planet. So settle in, allow your breathing to slow, and let the gentle rhythm of this narrative carry you through the vast, quiet expanses of space and time. There is no hurry here, no destination we must rush toward. We are simply wandering together through one of nature's most beautiful and ancient phenomena, letting curiosity guide us wherever it wishes to go. The story of meteors is, in many ways, the story of everything. It is a tale that begins in the swirling clouds of gas and dust that existed before our sun ignited, continues through billions of years of cosmic evolution, and extends into our present moment, where scientists work tirelessly to understand these messengers from the deep past. It is a story of violence and creation, of destruction and renewal, of the intricate dance between chaos and order that characterizes our universe. As we begin this journey, imagine yourself lying on soft grass on a warm summer evening, the dome of the sky stretching infinitely above you. The stars emerge slowly as twilight fades, first the brightest ones, then gradually more and more until the heavens seem dusted with silver light. And then without warning, a streak appears, a brief bright line drawn across the darkness, there and gone in the space of a breath. That momentary flash connects you to processes that began billions of years ago, to objects that have travelled distances almost impossible to comprehend, to the very forces that shaped our world and made your existence possible. This is the story we will explore together, from its most distant origins to its most intimate implications, and we will do so gently, peacefully, allowing each idea to unfold naturally, like petals opening in morning light. The earliest human records of meteor observations stretch back thousands of years, revealing how deeply these celestial events impressed themselves upon our ancestors' consciousness. In ancient China, court astronomers kept meticulous records of guest stars and falling stars, believing they carried messages about the fate of emperors and empires. The Bamboo Annals, dating to around 2000 BCE, contain some of the earliest written accounts of meteor showers, described with careful attention to their timing, direction, and apparent significance. Chinese scholars developed sophisticated systems for interpreting these events, categorizing them by color, brightness, and the region of sky from which they appeared. Across the ancient Near East, Babylonian astronomers similarly tracked celestial phenomena with remarkable precision. Clay tablets recovered from the ruins of Nineveh and other sites contain detailed observations of meteors, comets, and other transient events, often accompanied by interpretations of their meaning for kings and kingdoms. The Babylonians believed the sky was a kind of cosmic text, written by the gods for those wise enough to read it. Meteors, with their sudden appearance and dramatic brightness, were considered particularly significant messages, worthy of careful study and interpretation. In ancient Greece, philosophers began to move beyond purely mythological explanations, seeking natural causes for the phenomena they observed. Aristotle, writing in the 4th century BCE, proposed that meteors were an atmospheric phenomenon, caused by hot, dry exhalations from the earth that rose into the upper air and ignited. This explanation, though incorrect, represented an important step towards scientific thinking about these events. Aristotle's views dominated Western understanding of meteors for nearly 2,000 years, until careful observation and the scientific method revealed their true nature. The indigenous peoples of North America developed their own rich traditions surrounding meteors and meteor showers. Many tribes viewed falling stars as spirits travelling between the earthly and celestial realms, or as signs from ancestors and protective beings. The Pawnee people of the Great Plains held particularly elaborate beliefs about meteors, considering them to be messengers from the stars and incorporating meteor imagery into their sacred bundles and ceremonies. Some scholars have suggested that the Pawnees' detailed knowledge of meteor showers, particularly the Leonids, indicates centuries of careful observation passed down through oral tradition. In Australian Aboriginal cultures, meteors feature prominently in Dreamtime stories that explain the origins of landscape features and natural phenomena. Different Aboriginal groups developed distinct interpretations, with some viewing meteors as spirits of the deceased travelling to the sky world, while others saw them as fiery eyes of supernatural beings, or as implements thrown by sky ancestors. These stories, passed down through countless generations, represent some of humanity's oldest continuous traditions of meteor observation and interpretation. The ancient Egyptians associated meteors with the gods, particularly with the sky goddess Nut and the falcon-headed deity Horus. Meteoritic iron, recognizable by its distinctive crystalline structure and high nickel content, was highly prized by Egyptian craftsmen, who called it iron from the sky or metal of heaven. Archaeological discoveries have revealed that King Tutankhamun was buried with a dagger made from meteoritic iron, its blade still sharp after more than 3,000 years. This artifact speaks to the reverence with which ancient Egyptians regarded these gifts from the cosmos. Throughout medieval Europe, meteors continued to inspire wonder and fear in roughly equal measure. Church authorities often interpreted them as divine signs or warnings, while common folk developed extensive folklore around falling stars. The tradition of making a wish upon a shooting star, still practiced today, has roots in these medieval beliefs about the special power of such moments. Some medieval scholars, influenced by Aristotle's teachings, continued to view meteors as atmospheric phenomena, while others began to suspect they might have a more distant origin. The transition from mythological to scientific understanding of meteors occurred gradually over several centuries, accelerating dramatically in the late 18th and early 19th centuries. A crucial turning point came in 1794 when the German physicist Ernst Chladni published a revolutionary treatise arguing that meteorites were indeed stones that fell from space. Chladni's work was initially met with skepticism, even ridicule, from the scientific establishment. The idea that rocks could fall from the sky seemed absurd to many educated Europeans. Despite numerous eyewitness accounts and the existence of meteorite specimens in collections across the continent. The skepticism began to crumble in 1803 when a spectacular meteorite fall occurred near the town of L'Aigle in Normandy, France. Thousands of stones rained down over a wide area in broad daylight, witnessed by numerous credible observers. The French Academy of Sciences dispatched the young physicist Jean-Baptiste Biot to investigate, and his careful, systematic study of the evidence convinced even the most stubborn doubters that stones really did fall from the sky. Biot's report marked the beginning of meteoritics as a legitimate scientific discipline. As the 19th century progressed, scientists made rapid advances in understanding the nature and origin of meteors. The connection between meteor showers and comets was established when astronomers noticed that certain annual meteor displays seemed to originate from the same region of sky where comets had previously been observed. The Italian astronomer Giovanni Schiaparelli demonstrated in 1866 that the Perseid meteor shower was associated with Comet Swift-Tuttle, providing the first definitive link between these two types of celestial phenomena. The development of spectroscopy allowed scientists to analyze the light produced by meteors as they burned through the atmosphere, revealing information about their chemical composition. Photography enabled researchers to capture meteor trails and calculate their trajectories with unprecedented precision. By the early 20th century, the basic framework of modern meteor science was in place, though many details remain to be discovered. Today, our understanding of meteors continues to deepen through a combination of ground-based observation, space missions, and laboratory analysis of meteorite samples. We now know that these fleeting streaks of light connect us to the earliest history of our solar system, carrying information about conditions that existed billions of years before Earth formed. We have learned that meteorites come in many varieties, each type telling a different chapter of the cosmic story, and we have discovered that the same processes that create beautiful meteor showers have also played crucial roles in shaping the history of life on our planet. As we prepare to explore these topics in greater depth, let us carry with us an appreciation for the long human tradition of meteor watching. When we look up at the night sky and see a shooting star, we participate in an experience shared by countless generations before us. We stand in a line of observers stretching back to the very dawn of human consciousness, all of us united by wonder at these brief, beautiful visitors from the depths of space. The science we will discuss in the following sections is remarkable in its detail and sophistication, but it has not diminished the magic of meteors. If anything, understanding the true nature of these phenomena deepens our appreciation for them. Each meteor we see represents a journey of billions of years and millions of miles, a fragment of ancient history delivering itself to our doorstep in a flash of light. There is poetry in this, a kind of cosmic romance that scientific knowledge only enhances. So let us continue our journey together, moving now from the cultural and historical context into the realm of science. We will learn what meteors really are, where they come from, and what happens during those brief, brilliant moments when they grace our skies. And throughout, we will maintain the sense of wonder that has drawn human eyes skyward since the very beginning. To truly understand meteors, we must first untangle the terminology that surrounds them, for the words we use carry important distinctions. In everyday speech, people often use meteor, meteorite, and meteoroid interchangeably, but to scientists, each term has a precise meaning that reflects a different stage in the object's journey. A meteoroid is a small rocky or metallic body travelling through space. These objects range in size from tiny grains no larger than a speck of dust to boulders several meters across. Anything larger than about 1 meter is typically classified as an asteroid. though the boundary between large meteoroids and small asteroids is somewhat arbitrary. Meteoroids can be thought of as the cosmic raw material, the countless fragments of rock and metal that populate our solar system, remnants of its violent and creative youth. When a meteoroid enters Earth's atmosphere and begins to heat up due to friction with air molecules, it produces a visible streak of light that we call a meteor. This is the shooting star of common experience, the brief luminous trail that captures our attention and imagination. The meteor is not the object itself, but rather the phenomenon of light and heat produced by the object's passage through the atmosphere. Most meteors occur at altitudes between 80 and 120 kilometers above Earth's surface, in the region where the atmosphere becomes dense enough to create significant friction, but is still thin enough that the object hasn't been completely destroyed. If any portion of the meteoroid survives its fiery passage through the atmosphere and reaches Earth's surface, that surviving fragment is called a meteorite. Meteorites are the tangible evidence of cosmic visitors, physical samples of material from beyond our world that we can hold, study, and analyze. Not all meteors produce meteorites. In fact, the vast majority of meteoroids are too small to survive atmospheric entry. They burn up completely, their material dispersing as fine particles that eventually drift down to Earth's surface as cosmic dust. The distinction between these terms reflects the transformative nature of the meteor experience. A meteoroid can travel through space for millions or even billions of years, a cold, dark wanderer in the void. Its existence as a meteor lasts mere seconds, a brief blaze of glory as it encounters our atmosphere. And if it survives to become a meteorite, it enters a new phase of existence, resting on Earth's surface where it might be discovered by a curious human and subjected to scientific scrutiny. Understanding the physics of what creates a meteor helps us appreciate the remarkable nature of these events. When a meteoroid enters Earth's atmosphere at typical speeds of 11 to 72 kilometers per second, it collides with air molecules that, from the meteoroid's perspective, might as well be a wall. At these velocities, the air in front of the meteoroid cannot move out of the way fast enough. Instead, it becomes intensely compressed, and this compression generates tremendous heat. Contrary to popular belief, it is not primarily friction that heats the meteoroid, but rather this compression of air. The process is similar to what happens when you pump a bicycle tyre and feel the pump grow warm, but scaled up to extraordinary temperatures. The air immediately in front of the meteoroid can reach temperatures of several thousand degrees Celsius, hot enough to cause the surface of the meteoroid to melt and vaporize. This vaporized material, along with the superheated air, creates the glowing trail that we see as a meteor. The light comes from atoms that have been excited to high energy states by the intense heat and are releasing that energy as photons. Different elements produce different colors of light, which is why meteors can appear white, yellow, orange, green, or even blue, depending on their composition and the conditions of their entry. The process of material being stripped away from the meteoroid's surface is called ablation. As the outer layers vaporize, they carry away heat, actually protecting the interior of the meteoroid from the worst of the thermal assault. This ablative cooling is the same principle used in the heat shields of spacecraft returning to Earth. If a meteoroid is large enough and enters at the right angle, ablation can remove enough material to slow it down, while still leaving a substantial core intact to reach the surface as a meteorite. The brightness of a meteor depends on several factors, including the size of the meteoroid, its velocity, and its composition. Larger meteoroids naturally produce brighter meteors because there is more material available to vaporize. Faster meteoroids also tend to produce brighter meteors because the energy of the collision increases with the square of the velocity. A meteoroid travelling at 70 kilometers per second will produce a much more energetic entry than one travelling at 15 kilometers per second, even if they are the same size. Composition matters as well. Meteoroids rich in volatile elements or compounds will vaporize more readily, producing brighter meteors for their size. Iron meteoroids, being denser and more resistant to heating, tend to penetrate deeper into the atmosphere before producing their maximum brightness. The colour of the meteor provides clues about composition. Sodium produces yellow-orange light. Magnesium creates blue-green hues. Calcium contributes violet tones, and iron generates yellow light. Particularly bright meteors, those that outshine even the brightest planets, are called fireballs. The International Astronomical Union defines a fireball as a meteor brighter than magnitude -4, roughly equivalent to the brightness of Venus at its most brilliant. Fireballs can cast shadows and illuminate the landscape below, creating memorable experiences for those fortunate enough to witness them. Even brighter events, those that reach magnitude -14 or beyond, rivaling the full moon in brightness, are sometimes called bolides or superbolides. The most spectacular meteors can produce additional phenomena beyond simple light. Very bright fireballs sometimes generate sounds that reach the ground, either as delayed sonic booms arriving minutes after the visual display, or as mysterious sounds that seem to occur simultaneously with the meteor's appearance. These simultaneous sounds, called electrophonic sounds, puzzled scientists for many years. They are now thought to be caused by very low-frequency radio waves generated by the meteor, which can cause nearby objects to vibrate and produce audible sounds. Some bright meteors also leave persistent trains, glowing trails that remain visible for seconds or even minutes after the meteor itself has vanished. These trains are caused by atoms in the upper atmosphere that have been ionized and excited by the meteor's passage. As these atoms slowly return to their ground state, they continue to emit light, creating an eerie, slowly fading streak across the sky. Persistent trains can be affected by high-altitude winds, causing them to twist and distort into strange shapes as they dissipate. The height at which a meteor becomes visible and the height at which it extinguishes depend on several factors, but most meteors begin glowing at altitudes around 100 to 120 kilometers and fade out by about 80 kilometers. This region of the atmosphere, called the mesosphere, is where the air becomes dense enough to create significant heating. Faster meteoroids tend to begin glowing at higher altitudes because their greater kinetic energy allows them to heat the air even when it is relatively thin. The angle at which a meteoroid enters the atmosphere, called the entry angle or zenith angle, also affects the meteor's appearance. A meteoroid entering at a steep angle, nearly straight down, will pass through the atmosphere quickly, producing a short-lived but potentially very bright meteor. A meteoroid entering at a shallow angle, nearly horizontal, will have a much longer path through the atmosphere, producing a longer-lasting meteor that may travel across a significant portion of the sky. In extreme cases, meteoroids entering at very shallow angles may skip off the atmosphere entirely, like a stone skipping across water, continuing back into space without producing a meteorite fall. The typical meteor visible to the naked eye is produced by a meteoroid no larger than a grain of sand, perhaps a few millimeters across. It seems remarkable that such tiny objects can produce visible streaks of light, but the enormous velocities involved mean that even small masses carry substantial kinetic energy. A sand grain-sized meteoroid travelling at 50 kilometers per second has roughly the same kinetic energy as a bowling ball dropped from head height. When that energy is released in a fraction of a second, the result is a brief but impressive display. Larger meteoroids, those the size of pebbles or small rocks, produce proportionally brighter meteors. A meteoroid the size of a marble might produce a fireball visible across an entire state or country. A meteoroid the size of a basketball could produce a spectacular bolide that makes headlines and generates thousands of eyewitness reports. And truly large objects, those measuring meters or tens of meters across, can produce events of regional or even global significance. The rate at which meteoroids enter Earth's atmosphere varies depending on several factors, including the time of day, the season, and whether any meteor showers are active. On an average night, a patient observer under dark skies might see 5 to 10 sporadic meteors per hour. These sporadic meteors are random arrivals, not associated with any particular shower, representing the background flux of meteoroids that Earth continuously encounters as it orbits the Sun. During major meteor showers, the rate can increase dramatically, sometimes to hundreds of meteors per hour. In exceptional cases, during meteor storms, observers have reported seeing thousands of meteors per hour, so many that the sky seems to rain light. We will explore meteor showers in detail in a later section, but for now, it is enough to note that these events represent times when Earth passes through particularly dense concentrations of meteoroids, usually debris left behind by comets. The total amount of material that enters Earth's atmosphere each day is estimated at roughly 50 to 100 tons, though most of this mass arrives in the form of tiny particles too small to produce visible meteors. These micrometeorites, as they are called, drift slowly down through the atmosphere, eventually settling on Earth's surface. Over geological time, this constant rain of cosmic material has contributed significantly to Earth's mass and may have played important roles in delivering water and organic compounds to our young planet. Understanding the physics of meteors has practical applications beyond pure scientific curiosity. The same principles that govern meteor entry apply to spacecraft returning from orbit or from missions to other planets. Engineers designing heat shields must account for the intense temperatures generated by atmospheric entry, and they have learned much from studying how natural meteoroids behave during their fiery descents. The ablative heat shields used on early space capsules were directly inspired by observations of how meteoroids survive atmospheric entry. Meteor science also contributes to our understanding of planetary defense, the effort to protect Earth from potentially hazardous asteroids and comets. By studying how meteoroids of various sizes behave during atmospheric entry, scientists can better predict what would happen if a larger object were on a collision course with our planet. This knowledge helps inform decisions about how to respond to potential threats and how to design systems that might deflect or destroy dangerous objects before they reach Earth. As we conclude this section on the science of shooting stars, let us pause to appreciate the elegant simplicity underlying these complex phenomena. A meteor is, at its heart, a story of transformation. A cold, dark wanderer from the depths of space encounters the warm embrace of our atmosphere and is changed utterly in the process. Matter that has existed unchanged for billions of years is suddenly heated, melted, vaporized, and scattered across the sky in a display of light and colour. It is a kind of cosmic alchemy, turning ancient stone into momentary fire. And for us, the observers, each meteor offers a brief window into the vast and ancient universe beyond our world. The light that reaches our eyes carries information about the composition and origin of material formed before Earth existed. In that fraction of a second, we connect with processes that span billions of years and distances almost impossible to comprehend. There is something profound in this, something that transcends the technical details of atmospheric physics and spectroscopy. So the next time you see a shooting star, remember what you're witnessing. It is not merely a streak of light, but a messenger from the deep past, a fragment of the solar system's youth delivering itself to your doorstep in a blaze of glory. And though the physics may be well understood, the wonder remains undiminished. If anything, knowing what meteors really are makes them more marvellous, not less. To understand where meteors come from, we must journey back to the very beginning of our solar system, to a time before planets existed, before the sun had fully ignited, when all the matter that would eventually become our cosmic neighbourhood existed as a vast, slowly rotating cloud of gas and dust. This primordial cloud, called the solar nebula, contained the raw materials from which everything in our solar system would eventually form, including the meteoroids that still streak through our skies today. The solar nebula began to collapse under its own gravity roughly 4.6 billion years ago, possibly triggered by the shock wave from a nearby supernova explosion. As the cloud contracted, it began to spin faster, much as a figure skater spins faster when pulling in their arms. This rotation caused the cloud to flatten into a disc shape, with most of the mass concentrating at the centre where it would eventually form the sun. Within this spinning disk, tiny particles of dust began to stick together when they collided, gradually building up larger and larger clumps. This process, called accretion, was slow at first, but it accelerated as the growing clumps developed stronger gravitational pulls. Over millions of years, these clumps grew into planetesimals, objects ranging from meters to kilometers in size that represent the building blocks of planets. Some planetesimals continue to grow, sweeping up material from their surroundings and eventually becoming the planets we know today. But not all planetesimals shared this fate. Many were destroyed in collisions with larger bodies, shattered into fragments that were scattered throughout the solar system. Others were flung into different orbits by gravitational interactions with the growing planets, particularly the massive giant planets like Jupiter. And some simply remained in regions of the solar system where conditions prevented them from growing further. The meteoroids that produce today's meteors come from several distinct populations, each with its own origin story. The largest source of meteoroids is the asteroid belt, a region between the orbits of Mars and Jupiter where millions of rocky bodies orbit the Sun. These asteroids are the remnants of planetesimals that never managed to coalesce into a planet, their growth stunted by the gravitational influence of nearby Jupiter. The asteroid belt is not the peaceful, static place that early science fiction imagined. Collisions between asteroids occur regularly, shattering larger bodies and producing countless smaller fragments. These fragments can be ejected from the belt through various mechanisms, including gravitational interactions with Jupiter and other planets, and some eventually find their way into orbits that cross Earth's path. When these fragments enter our atmosphere, they become the meteors we observe. Different types of asteroids produce different types of meteoroids. Some asteroids are composed primarily of silicate minerals, similar to rocks found on Earth. Others are rich in carbon compounds and water, representing some of the most primitive material in the solar system. A smaller number are composed largely of iron and nickel, the cores of larger bodies that were shattered by ancient collisions. The meteorites that reach Earth's surface reflect this diversity, providing scientists with samples of many different asteroid types. A second major source of meteoroids is comets, those spectacular visitors from the outer solar system that develop glowing tails when they approach the Sun. Comets are fundamentally different from asteroids in their composition and origin. While asteroids are rocky bodies that formed in the inner solar system, comets are icy bodies that formed in the cold outer reaches beyond the orbit of Neptune. Comets are often described as dirty snowballs or icy dirt balls, reflecting their composition of water ice, frozen gases, and rocky or dust-type particles. When a comet approaches the Sun, the heat causes the ice to sublimate, transforming directly from solid to gas without passing through a liquid phase. This outgassing carries dust and rocky particles away from the comet's nucleus, creating the spectacular tail that makes comets so visually striking. The particles released by comets do not simply disappear. They continue to orbit the Sun, gradually spreading out along the comet's orbital path. Over many orbits, the debris forms a stream of particles that traces the comet's trajectory through space. When Earth's orbit intersects one of these debris streams, we experience a meteor shower, with numerous meteors appearing to radiate from a single point in the sky. The connection between comets and meteor showers was one of the great discoveries of 19th century astronomy. When Giovanni Schiaparelli demonstrated that the Perseid meteor shower was associated with comet Swift-Tuttle, he revealed a fundamental truth about the nature of these annual displays. Since then, astronomers have identified the parent comets of many major meteor showers, though some showers are associated with comets that have long since disintegrated or with asteroid-like objects that may be extinct comets. Cometary meteoroids tend to be fragile, loosely bound collections of dust and ice. When they enter Earth's atmosphere, they typically disintegrate completely, producing bright meteors but rarely surviving to reach the surface as meteorites. This fragility reflects their icy origins and the relatively gentle conditions under which they formed in the outer solar system. A third source of meteoroids, smaller in total contribution but fascinating in its implications, is the Moon and Mars. When large impacts occur on these bodies, they can eject material with enough velocity to escape the body's gravity. Some of this ejected material eventually finds its way to Earth, where it falls as meteorites. Lunar and Martian meteorites are rare and precious, providing scientists with samples of these worlds without the need for expensive sample return missions. The identification of lunar and Martian meteorites relies on detailed chemical and isotopic analysis. Lunar meteorites can be compared with samples returned by the Apollo missions, while Martian meteorites contain trapped gases that match the composition of Mars's atmosphere as measured by spacecraft. These meteorites have provided valuable insights into the geology and history of both worlds. The journey from source region to Earth can take many different paths and timescales. Some meteoroids travel relatively directly, their orbits perturbed by gravitational interactions until they intersect Earth's path. Others may spend millions of years in the asteroid belt before a collision or gravitational nudge sends them sunward. And some meteoroids may orbit the Sun for billions of years before finally encountering our planet. The orbits of meteoroids can be calculated by observing the meteors they produce. By photographing or videoing a meteor from multiple locations, scientists can triangulate its path through the atmosphere and work backward to determine its orbit before it encountered Earth. These observations have confirmed that most meteoroids come from the asteroid belt, with smaller contributions from cometary sources and other regions. The Poynting-Robertson effect plays an important role in the evolution of meteoroid orbits over long timescales. This subtle effect arises from the interaction between sunlight and small particles. As a particle absorbs sunlight and re-emits it as thermal radiation, the radiation carries away a tiny amount of momentum. Over millions of years, this momentum loss causes the particle's orbit to slowly spiral inward toward the Sun. The Poynting-Robertson effect is more significant for smaller particles, which is why the smallest meteoroids tend to have orbits closer to the Sun. Gravitational interactions with planets, particularly Jupiter, are the dominant force shaping meteoroid orbits on shorter timescales. Jupiter's immense gravity can dramatically alter the orbits of small bodies that pass nearby, either flinging them out of the solar system entirely or redirecting them into new orbits that may bring them closer to Earth. The so-called Kirkwood gaps in the asteroid belt, regions where few asteroids are found, mark orbital resonances with Jupiter where gravitational perturbations are particularly strong. The Yarkovsky effect is another subtle but important force affecting meteoroid orbits. This effect arises because rotating bodies absorb sunlight on one side and re-emit it as heat on another side after the body has rotated. The resulting asymmetric radiation creates a tiny thrust that can gradually change the body's orbit over millions of years. The Yarkovsky effect is most significant for objects in the meter to kilometer size range and plays an important role in delivering asteroids from the main belt to Earth-crossing orbits. Understanding the sources and dynamics of meteoroids has practical implications for planetary defense. By knowing where potentially hazardous objects come from and how their orbits evolve, scientists can better predict which objects might pose future threats to Earth. The same gravitational mechanisms that deliver small meteoroids to our planet could also deliver larger, more dangerous objects, making this knowledge crucial for protecting our world. The diversity of meteoroid sources means that the meteors we observe carry information about many different environments and epochs. A meteor produced by a cometary particle tells us about conditions in the outer solar system, where ice and volatile compounds could survive. A meteor from an asteroidal source tells us about the rocky inner solar system and the processes that shape the planets. And rare meteors from the Moon or Mars provide glimpses of worlds that humans have barely begun to explore. As we contemplate the origins of meteors, we are reminded of the deep interconnectedness of our solar system. The same processes that form the planets also produce the countless small bodies that continue to orbit the Sun today. The same gravitational forces that keep Earth in its stable orbit also perturb the paths of meteoroids, occasionally sending them our way. And the same cosmic violence that shattered ancient planetesimals continues today, producing fresh debris that will eventually become tomorrow's meteors. In this sense, every meteor we observe is a link to the past, a fragment of history delivered across billions of miles and billions of years. The flash of light we see represents the end of a journey that began before Earth existed in the swirling chaos of the solar nebula. And though the journey ends in destruction, the information carried by that light lives on, adding to our understanding of the cosmos and our place within it. The journey of a meteoroid through space is one of profound stillness and patience, a voyage measured not in days or years, but in millions or billions of years. To truly appreciate what happens when a meteor streaks across our sky, we must first understand the immense journey that preceded that brief, brilliant moment. Consider a typical meteoroid, perhaps a fragment of an asteroid knocked loose by a collision in the main belt some 50 million years ago. At the moment of its creation, it was part of a larger body, locked in place by the parent asteroid's gravity and sharing its orbit around the Sun. The collision that freed it was violent and sudden, lasting perhaps only seconds, but it imparted enough velocity to send our fragment spinning away into space on its own independent path. In those first moments after the collision, our meteoroid was surrounded by countless siblings, other fragments from the same impact event ranging in size from microscopic dust to boulders several meters across. But space is vast, and even this dense cloud of debris quickly dispersed. Within days, our meteoroid found itself alone, tumbling slowly through the void, with no companion closer than thousands of kilometers. The orbit our meteoroid inherited from its parent asteroid was not quite the same as the original. The impact imparted a small change in velocity, nudging the meteoroid onto a slightly different path. This new orbit might be a bit more elongated or tilted at a slightly different angle to the plane of the solar system. These small differences would prove crucial over the eons to come. For millions of years, our meteoroid followed its new orbit with mechanical precision, looping around the Sun again and again. Each orbit took perhaps 4 or 5 years to complete, depending on its distance from the Sun. During this time, the meteoroid experienced almost nothing. No air resistance slowed its motion. No sound broke the silence. The only forces acting upon it were the gentle, persistent tug of gravity and the subtle pressure of sunlight. The surface of our meteoroid bore the scars of its violent birth, fresh fractures and sharp edges that would slowly change over time. Cosmic rays, high-energy particles streaming through space from distant supernovae and other violent events bombarded the meteoroid continuously, penetrating its surface and causing subtle changes in its crystal structure. These cosmic ray tracks would later provide scientists with a way to determine how long the meteoroid had been exposed to space, a kind of cosmic clock ticking away in the rock itself. Micrometeorites, tiny particles even smaller than our meteoroid, occasionally struck its surface at tremendous velocities. Each impact created a miniature crater, sometimes no larger than a pinprick, but over millions of years, these impacts accumulated, gradually smoothing the sharp edges left by the original collision. The surface developed a texture unlike anything found on Earth, a record of countless tiny collisions written in microscopic pits and glass-lined craters. The temperature of our meteoroid varied as it orbited the Sun, warming slightly during the closer portions of its orbit and cooling as it swung outward toward the realm of Jupiter. But even at its warmest, the meteoroid remained far colder than any natural environment on Earth. In the vacuum of space, with no atmosphere to retain heat, the side facing the Sun might warm to modest temperatures, while the shadowed side remained bitterly cold. This constant cycling between warm and cold, repeated millions of times, may have caused subtle stresses in the rock, preparing it for the eventual fragmentation that would occur during atmospheric entry. For most of its journey, our meteoroid travelled in splendid isolation. The distances between objects in space are so vast that encounters with other bodies were extraordinarily rare. Occasionally, our meteoroid might pass within a few thousand kilometres of another asteroid, close enough to feel a slight gravitational tug, but far too distant for any direct interaction. These encounters were mere whispers in the cosmic silence, brief gravitational handshakes between strangers passing in the night. But gravity, though gentle, is persistent. Each encounter with another body, each passage near a planet, left its mark on our meteoroid's orbit. The changes were tiny, almost imperceptible, but they accumulated over time. Like a pinball, bouncing slowly between bumpers, our meteoroid's path gradually shifted, its orbit becoming more elongated, its closest approach to the Sun creeping ever inward. Jupiter, the giant of our solar system, played a particularly important role in shaping our meteoroid's destiny. Even from hundreds of millions of kilometres away, Jupiter's immense gravity exerted a measurable influence. When our meteoroid's orbital period happened to be a simple fraction of Jupiter's, a resonance developed that amplified the gravitational effects. Over millions of years, these resonances pumped energy into our meteoroid's orbit, stretching it into an increasingly elongated ellipse. The process was neither steady nor predictable. Sometimes our meteoroid's orbit would remain stable for millions of years, then suddenly shift dramatically due to a particularly close approach to a planet or a chance alignment of gravitational forces. The solar system, though it appears orderly on human timescales, is actually chaotic over longer periods. Small differences in initial conditions can lead to vastly different outcomes, making the long-term fate of any individual meteoroid essentially unpredictable. As our meteoroid's orbit became more elongated, it began to cross the paths of the inner planets. First Mars, then Earth, then perhaps even Venus came within reach of its wandering trajectory. Each orbit now carried our meteoroid through regions of space it had never visited before, past worlds it had never seen. The Sun once a distant lamp, now loomed larger during the close portions of its orbit, warming the ancient rock more than it had been warmed in billions of years. The crossing of planetary orbits marked a new and more dangerous phase of our meteoroid's existence. While the chances of actually striking a planet remained small on any given orbit, the cumulative probability grew with each passage. Our meteoroid had entered a kind of cosmic lottery, and eventually the odds would catch up with it. During this phase, our meteoroid might have had close encounters with Earth that did not result in collision. Perhaps it passed within the Moon's orbit, close enough that careful observers with telescopes might have spotted it as a faint, fast-moving point of light. Perhaps it even grazed Earth's atmosphere, skipping off the upper layers like a stone skipping across water, briefly heating before continuing on its way. Such grazing encounters are not common, but they do occur, and they can dramatically alter a meteoroid's orbit. The final approach, when it came, was not dramatically different from countless previous orbits. Our meteoroid swung around the Sun, climbed back out toward the asteroid belt, then fell sunward once more. But this time, Earth happened to be in exactly the wrong place at exactly the wrong time. The geometry that had kept them apart for 50 million years finally aligned in a way that made collision inevitable. Even in these final days, the meteoroid remained unaware of its approaching fate. It had no senses, no consciousness, no way to perceive the blue-white world growing slowly larger in its path. It simply followed the trajectory that gravity had carved for it, as it had done for millions of years. The laws of physics that had governed its entire existence would now bring that existence to a spectacular end. The transition from deep space to atmospheric entry happened with surprising swiftness. One moment, our meteoroid was coasting through the vacuum. The next, it was encountering the first tenuous wisps of Earth's upper atmosphere. At an altitude of perhaps 200 kilometers, the air was still incredibly thin, less than a billionth of the density at sea level. But at the meteoroid's velocity, even this faint trace of atmosphere began to make itself felt. The first indication of atmospheric entry was a faint glow, barely visible, as air molecules began to be compressed and heated in front of the meteoroid. This glow intensified rapidly as the meteoroid descended into denser air. Within seconds, the ancient rock that had travelled in cold darkness for 50 million years was surrounded by a sheath of plasma hotter than the surface of the sun. The violence of this transition is difficult to overstate. Forces that would crush any human-made structure tore at the meteoroid's surface. Temperatures that would vaporize steel began to eat away at the rock. The patient accumulation of cosmic ray tracks and micrometeorite craters, the record of 50 million years of space exposure, was erased in moments as the outer layers ablated away. And yet in this destruction there was creation. The light produced by our meteoroid's demise carried information about its composition across hundreds of kilometers to the eyes of observers below. The atoms that had been locked in crystal structures for billions of years were released to join Earth's atmosphere, eventually to be incorporated into clouds, rain, plants, and perhaps even living creatures. The meteoroid's long journey was ending, but its matter would continue on in new forms. For observers on the ground, the whole event lasted perhaps 2 or 3 seconds. A bright streak appeared in the sky, travelled across a portion of the heavens, and vanished. Some might have made a wish. Others might have simply noted the sight and continued with their evenings. Few would have paused to consider the immense journey that had just concluded, the billions of orbits and millions of years that had preceded that brief flash of light. If our meteoroid was large enough, and if conditions were right, a fragment might have survived to reach the surface. This surviving piece, now called a meteorite, would carry within it a record of everything that had happened. The formation in the solar nebula, the accretion into a larger body, the catastrophic collision that set it free, the long journey through space, and the fiery passage through the atmosphere. All of this history encoded in the rock's chemistry and structure, waiting to be read by curious scientists. But even if nothing survived, even if our meteoroid was completely destroyed in the atmosphere, its story was not truly over. The energy of its passage created disturbances in the upper atmosphere that would persist for hours. The atoms it released would eventually settle to Earth's surface, adding their mass to our planet. And the light of its passage, travelling outward at the speed of light, would continue forever into the universe, a final testament to a journey of cosmic proportions. This is the story of every meteor we see, though the details vary endlessly. Some meteoroids are older, some younger. Some come from asteroids, others from comets. Some travel relatively short distances, others cross the entire solar system. But all share this basic narrative arc: formation, journey, transformation. It is a story written in fire and light, played out against the backdrop of the infinite cosmos. As we prepare to explore the physics of atmospheric entry in greater detail, carry with you this sense of the journey that precedes each meteor. The streak of light you see is not an isolated event, but the culmination of a voyage almost incomprehensible in its duration and distance. Every shooting star is a traveller arriving home after an absence of millions or billions of years, announcing its arrival in the only way it can, with a brief, brilliant blaze of glory. Chapter 5: Atmospheric Entry, the Physics of the Streak. We have followed our meteoroid through the vast emptiness of space, traced its origins to the violent birth of the solar system, and watched as gravitational forces slowly shaped its orbit over millions of years. Now we arrive at the climactic moment, the few seconds of intense activity that transform a cold, dark wanderer into the brilliant streak of light we call a meteor. This transformation involves some of the most extreme physics found anywhere in nature, and understanding it reveals just how remarkable these everyday celestial events truly are. The Earth's atmosphere, which we often take for granted, is a complex, layered structure that extends hundreds of kilometres above the surface. At sea level, we live at the bottom of an ocean of air, where the pressure is about 101 kilopascals and the density is roughly 1.2 kilograms per cubic metre. But as we ascend, both pressure and density decrease rapidly. By the time we reach the altitude where most meteors occur, around 80 to 120 kilometres, the air is so thin that it would be considered a fairly good vacuum by laboratory standards. Yet even this tenuous atmosphere is enough to stop most meteoroids in their tracks. The key is velocity. Meteoroids enter Earth's atmosphere at speeds ranging from about 11 kilometers per second, the minimum required to reach Earth from elsewhere in the solar system, to about 72 kilometers per second, the maximum possible for an object in a bound orbit around the Sun. These velocities are almost impossible to visualize. A rifle bullet travels at roughly 1 kilometer per second. A meteoroid at the slow end of the range is moving 11 times faster than that. A fast meteoroid is moving more than 70 times faster. At these speeds, the behavior of air changes dramatically. In everyday experience, air flows smoothly around moving objects, creating gentle pressure differences that we feel as wind. But when an object moves faster than the speed of sound, around 343 meters per second at sea level, the air cannot get out of the way fast enough. Instead, it piles up in front of the object, creating a shock wave. This is the source of the sonic boom produced by supersonic aircraft. Meteoroids move not just faster than sound, but many times faster. They are not merely supersonic but hypersonic, a regime where the physics becomes even more extreme. At hypersonic speeds, the air in front of the meteoroid is compressed so violently that it heats to temperatures of tens of thousands of degrees. This is not friction in the conventional sense, though that term is often used loosely. Rather, It is the conversion of the meteoroid's kinetic energy into thermal energy through compression and shock heating. The temperature of the compressed air can exceed 20,000 degrees Celsius, far hotter than the surface of the Sun. At these temperatures, air molecules are torn apart into their constituent atoms, and those atoms are stripped of their electrons, creating a plasma. This plasma surrounds the meteoroid in a glowing sheath, producing the light that we see from the ground. The colour and intensity of this light depend on the temperature of the plasma and the elements present, both from the air and from the vaporizing meteoroid. The meteoroid itself is protected to some extent by the very plasma that surrounds it. The extremely hot gas creates a buffer zone that prevents direct contact between the meteoroid's surface and the worst of the shock-heated air. Heat is transferred to the meteoroid primarily through radiation from the plasma and through direct contact at the boundary layer. This heating causes the outer surface of the meteoroid to melt and vaporize, a process called ablation. Ablation is both destructive and protective. As the surface material vaporizes, it carries away enormous amounts of heat, preventing that energy from penetrating deeper into the meteoroid. This is the same principle used in the heat shields of spacecraft, which are designed to ablate during re-entry, sacrificing their outer layers to protect the vehicle and its occupants. Nature discovered this solution billions of years before human engineers reinvented it. The rate of ablation depends on many factors, including the meteoroid's velocity, its composition, and its shape. Faster meteoroids experience more intense heating and ablate more rapidly. Meteoroids made of volatile materials vaporize more easily than those made of refractory minerals, and the shape of the meteoroid affects how the shock wave forms around it, influencing the distribution of heating across its surface. As material ablates from the meteoroid's surface, it joins the plasma sheath, adding its own characteristic emissions to the light we observe. Different elements produce light at different wavelengths, giving meteors their varied colours. Sodium, which is common in many meteoroids, produces a bright yellow-orange emission. Magnesium creates a blue-green colour. Iron contributes yellow light. Calcium adds violet hues. By analysing the spectrum of a meteor's light, scientists can determine what elements are present and in what proportions. The trail left behind a meteor is not simply hot air, but a column of ionized gas, a plasma tube stretching across the sky. This ionization is caused by the intense heat and by ultraviolet radiation from the plasma sheath. The ionized trail can persist for seconds or even minutes after the meteor itself has vanished, slowly cooling and recombining as the ions capture electrons and return to their neutral state. These ionized trails have practical applications beyond pure science. Radio waves can bounce off the ionized columns, allowing for a form of communication called meteor burst communication. This technique has been used for military and scientific purposes, taking advantage of the brief windows when meteor trails provide a reflective path between distant stations. The trails can also be detected by radar, allowing scientists to study meteors that occur during daylight or under cloudy skies when visual observation is impossible. The deceleration experienced by a meteoroid during atmospheric entry is extreme by any standard. A typical meteoroid might slow from 30 kilometers per second to essentially zero in just a few seconds, experiencing average decelerations of thousands of Gs. The peak deceleration can be even higher, reaching tens of thousands of Gs during the most intense phase of entry. No human-made structure could survive such forces intact. For meteoroids, this deceleration often leads to fragmentation. The combination of aerodynamic forces, thermal stresses, and internal weaknesses causes many meteoroids to break apart during entry. A single incoming object might shatter into dozens or hundreds of pieces, each following its own trajectory through the atmosphere. This fragmentation can produce spectacular visual effects, with multiple parallel trails or a sudden brightening as fresh surface area is exposed to heating. The altitude at which a meteor reaches maximum brightness depends on its initial velocity and the angle of entry. Faster meteoroids tend to reach maximum brightness at higher altitudes because they deposit their energy more rapidly. Meteoroids entering at shallow angles have longer path lengths through the atmosphere and may reach maximum brightness at lower altitudes. The typical meteor reaches peak brightness somewhere between 80 and 95 kilometers altitude. Below this peak, the meteor typically fades rapidly. The meteoroid has lost most of its velocity and mass to ablation, and the reduced speed means less intense heating. If any significant fragment survives to this point, it enters a phase called dark flight, falling through the lower atmosphere without producing visible light. During dark flight, the fragment continues to slow due to air resistance, eventually reaching a terminal velocity determined by its size, shape, and density. The transition from luminous flight to dark flight marks a critical boundary. Above this boundary, the meteoroid is a meteor, a streak of light in the sky. Below it, the surviving fragment is simply a falling rock, no longer producing the characteristic glow. The altitude of this transition varies but is typically around 20 to 30 kilometers for meteoroids that produce recoverable meteorites. During dark flight, the falling fragment cools rapidly. The outer surface, which moments ago was at thousands of degrees, radiates its heat into the surrounding air. By the time the fragment reaches the ground, it may be merely warm to the touch, or even cold if it has fallen from high altitude, where the air itself is extremely cold. This is why freshly fallen meteorites are not the burning hot rocks of popular imagination. The brief heating during entry affects only a thin outer layer, while the interior remains at the cold temperatures of deep space. The final impact with the ground is anticlimactic compared to the drama of atmospheric entry. A typical meteorite strikes the surface at perhaps 100 to 200 meters per second, fast enough to be dangerous, but far slower than its original cosmic velocity. The impact creates a small crater or simply embeds the meteorite in soft ground. Large meteorites can create more significant craters, but even these are modest compared to what would result if the full cosmic velocity were retained. The entire process, from first atmospheric contact to final impact, typically takes less than a minute for meteoroids that produce recoverable meteorites. For smaller meteoroids that burn up completely, the luminous phase lasts only a few seconds. Yet in this brief time, an object that has existed unchanged for billions of years is transformed utterly, its outer layers vaporized, its interior stressed and fractured, its cosmic journey brought to a sudden end. For scientists, the physics of atmospheric entry is a rich field of study with applications far beyond meteoritics. Understanding how objects behave during hypersonic flight is crucial for designing spacecraft that can safely return to Earth or land on other planets with atmospheres. The same principles that govern meteor entry apply to capsules carrying astronauts, probes descending to Mars or Venus, and even to the re-entry of space debris. The study of meteors has also contributed to our understanding of Earth's upper atmosphere. By observing how meteors behave at different altitudes, scientists can infer the density and composition of air in regions that are difficult to study by other means. The trails left by meteors provide information about high-altitude winds and temperatures. In this way, meteors serve as natural probes of the atmosphere, providing data that complements measurements from rockets and satellites. As we conclude this exploration of atmospheric entry, let us pause to appreciate the violence and beauty intertwined in these events. A meteor is a kind of cosmic sacrifice, an ancient traveller giving up its existence in a blaze of light. The energy that produces this light was accumulated over billions of years, stored in the meteoroid's motion through space. In a few seconds, all of that energy is released, converted into heat, light, and the kinetic energy of atmospheric gases. Yet from this destruction comes knowledge. The light of a meteor carries information about the composition of material formed before Earth existed. The meteorites that survive to reach the surface are samples of other worlds delivered to us free of charge. And the process of entry itself reveals secrets about our atmosphere and the physics of hypersonic flight. In death, the meteor gives gifts that enrich our understanding of the cosmos. The next time you see a shooting star, consider the physics unfolding in that brief streak of light. Consider the temperatures hotter than the sun's surface, the forces that would crush any human creation, the ancient rock being transformed into plasma and light. And consider that this violent process, repeated countless times each day around our planet, is one of the ways the universe communicates with us, sending messengers from the distant past to illuminate our present skies. Chapter 6: Meteor Showers, the Annual Celestial Celebrations. Throughout human history, certain nights have been marked by unusual activity in the heavens, times when meteors appear not singly, but in abundance, streaming across the sky like rain from the stars. These meteor showers have inspired wonder, fear, and scientific curiosity in equal measure. They represent some of the most predictable and accessible astronomical events, requiring no special equipment to observe, only clear skies and patience. Understanding meteor showers opens a window into the dynamic processes that shape our solar system and connects us to the comets and asteroids that share our cosmic neighbourhood. A meteor shower occurs when Earth passes through a stream of debris left behind by a comet, or, less commonly, an asteroid. Unlike the sporadic meteors that can appear from any direction, at any time, shower meteors all seem to radiate from a single point in the sky, called the radiant. This apparent radiation is a perspective effect, similar to how parallel railroad tracks seem to converge in the distance. The meteoroids in a shower are actually travelling in parallel paths, but their trails appear to diverge from the radiant when viewed from Earth. The radiant gives each meteor shower its name. The Perseids appear to radiate from the constellation Perseus. The Leonids seem to emerge from Leo. The Geminids stream from Gemini. This naming convention allows observers to immediately identify which shower a particular meteor belongs to, simply by tracing its path backward to see which radiant it originated from. The debris streams that produce meteor showers are the legacy of comets that have passed through the inner solar system. Each time a comet approaches the sun, the heat causes its icy surface to sublimate, releasing gas and dust into space. This material does not simply vanish but continues to orbit the sun, gradually spreading out along the comet's orbital path. Over many orbits, the debris forms a stream that can stretch completely around the sun, a river of particles tracing the comet's trajectory through space. When Earth's orbit intersects one of these debris streams, we experience a meteor shower. The timing of the intersection determines when the shower occurs each year, which is why meteor showers happen at the same time annually. The Perseids always peak around August 11 to 13 because that is when Earth crosses the debris stream of comet Swift-Tuttle. The Geminids always peak around December 13 to 14 because that is when we encounter the debris from asteroid 3200 Phaethon. The intensity of a meteor shower depends on several factors. The density of the debris stream matters enormously. Streams that have been refreshed recently by an active comet tend to be denser than those from comets that have long since faded or disintegrated. The geometry of the intersection also plays a role. If Earth passes through the centre of the stream, we see more meteors than if we merely graze its edge. And the age of the stream affects its structure. Young streams tend to be narrow and concentrated, while older streams spread out and become more diffuse. The Perseid meteor shower is perhaps the most beloved of all annual showers, at least in the Northern Hemisphere. Occurring in the warm nights of August, when many people are on vacation and inclined to spend time outdoors, the Perseids offer a reliable display of 50 to 100 meteors per hour under ideal conditions. The shower has been observed for at least 2,000 years, with Chinese records from 36 CE describing meteors streaming from the direction of Perseus. The parent body of the Perseids is Comet 109P Swift-Tuttle, a large comet with a nucleus estimated at about 26 kilometers in diameter. Swift-Tuttle has an orbital period of roughly 133 years, most recently passing through the inner solar system in 1992. Each perihelion passage refreshes the debris stream, ensuring that the Perseids will remain active for centuries to come. The comet itself has been observed since at least 69 BCE, making it one of the longest observed periodic comets. Perseid meteors are known for their brightness and their tendency to produce fireballs. This is partly because the debris particles from Swift-Tuttle are relatively large, and partly because the shower occurs when Earth is moving into the debris stream, increasing the collision velocity. The combination of large particles and high velocity produces particularly energetic entries, resulting in bright, often colourful meteors that can leave persistent trains. The Geminid meteor shower, peaking in mid-December, has become the most prolific annual shower, regularly producing 120 to 150 meteors per hour under optimal conditions. Unlike most meteor showers, the Geminids are associated not with a comet, but with an asteroid, 3200 Phaethon. This unusual parent body has sparked considerable scientific interest, as asteroids are not normally expected to produce the kind of debris streams that create meteor showers. Phaethon is classified as a rock comet, an asteroid that exhibits some comet-like behaviour. Its orbit carries it closer to the Sun than any other named asteroid, with a perihelion distance of just 0.14 astronomical units. At this close approach, the surface temperature exceeds 700 degrees Celsius, hot enough to cause thermal fracturing and the release of dust particles. This process, rather than the sublimation of ice that drives cometary activity, is thought to be responsible for the Geminid debris stream. Geminid meteors tend to be slower than Perseids, entering the atmosphere at about 35 kilometers per second compared to 59 kilometers per second for Perseids. This lower velocity results from the geometry of the encounter and the orbit of the parent body. Despite their slower speed, Geminid meteors are often bright and can display a range of colours, including white, yellow, and occasionally blue or green. The Leonid meteor shower holds a special place in the history of meteor science. While the annual Leonids are modest, producing perhaps 15 meteors per hour in a typical year, the shower is capable of producing spectacular storms when Earth passes through particularly dense portions of the debris stream. These storms have occurred roughly every 33 years, corresponding to the orbital period of the parent comet, 55P Tempel-Tuttle. The Leonid storm of 1833 was one of the most spectacular astronomical events in recorded history. Observers across North America witnessed an estimated 100,000 meteors per hour, so many that the sky seemed to be raining stars. This event had a profound impact on both public awareness and scientific understanding of meteors. It demonstrated conclusively that meteors came in streams associated with specific radiance, and it sparked the research that would eventually link meteor showers to comets. Subsequent Leonid storms occurred in 1866, 1966, and 1999 to 2002, though none quite matched the intensity of the 1833 event. The 1966 storm was particularly impressive, with observers in the western United States reporting rates of up to 150,000 meteors per hour for a brief period. The 1999 to 2002 storms, while less intense, were the first to be studied with modern instruments, providing valuable data about the structure and evolution of the debris stream. The quadrantid meteor shower, peaking around January 3 to 4, is notable for having the shortest peak of any major shower. While the Perseids and Geminids produce elevated rates for several days around their maximum, the quadrantid peak lasts only about 6 hours. This narrow peak results from the compact nature of the debris stream, which has not had time to spread out significantly. The parent body of the quadrantids is somewhat mysterious. The shower is associated with asteroid 2003 EH1, which may be an extinct comet or a fragment of a comet that broke apart several centuries ago. Some researchers have linked the quadrantids to comet C1490Y1 observed by Chinese, Japanese, and Korean astronomers in 1490. If this connection is correct, the quadrantid debris stream is relatively young, explaining its compact structure. The Eta Aquarid and Orionid meteor showers share a common parent, the famous comet 1P Halley. The Eta Aquarids occur in early May, when Earth passes through one portion of Halley's debris stream, while the Orionids occur in late October, when we encounter another portion. Both showers produce fast meteors, entering the atmosphere at about 66 kilometers per second, among the fastest of any annual shower. Halley's comet has been observed for over 2,000 years, with records dating back to at least 240 BCE. Its 76-year orbital period has allowed many generations to witness its apparitions, and the debris it has shed over millennia has created two substantial meteor streams. The Eta Aquarids can produce up to 50 meteors per hour, while the Orionids typically yield about 20 per hour, though both showers are subject to considerable variation. The Taurid meteor shower is unusual in several respects. Rather than a brief intense peak, the Taurids produce a prolonged period of activity stretching from September through November. The shower actually consists of two branches, the southern Taurids and the northern Taurids, with peaks about 2 weeks apart. Taurid meteors are slow and often bright, with a higher than average proportion of fireballs. The Taurid complex is associated with comet 2P Encke, which has the shortest orbital period of any known comet at just 3.3 years. The debris stream is ancient and spread out, which explains the shower's extended duration. Some researchers have proposed that the Taurid complex may contain larger objects, including asteroids several hundred meters in diameter, raising the possibility of significant impacts during Taurid season. This hypothesis remains controversial, but has attracted serious scientific attention. The Lyrid meteor shower, occurring in late April, is one of the oldest known meteor showers, with Chinese records of its activity dating back to 687 BCE. The parent body is comet C1861 G1 Thatcher, which has an orbital period of about 415 years. The Lyrids typically produce 15 to 20 meteors per hour, though occasional outbursts have yielded much higher rates. In 1982, observers reported brief rates of up to 90 meteors per hour. The Delta Aquarid meteor shower peaks in late July, providing a warm-up for the Perseids that follow a few weeks later. The shower produces about 20 meteors per hour and is best viewed from the southern hemisphere, where the radiant rises higher in the sky. The parent body is uncertain, with several comets proposed as possible sources. Beyond these major showers, dozens of minor showers occur throughout the year, each associated with its own debris stream and parent body. Some of these minor showers are well established, with centuries of observations, while others have been identified only recently through careful analysis of meteor data. The International Astronomical Union maintains an official list of meteor showers, which currently includes over 100 established showers and hundreds of additional candidates awaiting confirmation. The study of meteor showers has advanced significantly with the development of automated observation systems. Networks of cameras continuously monitor the sky, recording meteors and calculating their trajectories with high precision. These observations allow scientists to map the structure of debris streams in unprecedented detail, revealing clumps and filaments that produce the variations in shower intensity from year to year. Radar observations complement visual and photographic techniques, allowing meteors to be detected during daylight and through cloud cover. Several major meteor showers have radiants that are above the horizon, primarily during daylight hours, making them difficult or impossible to observe visually. Radar studies have revealed these daylight showers, including the Areatids in June, which may actually be the most prolific meteor shower of the year, despite being largely invisible to the naked eye. Space-based observations have added another dimension to meteor shower research. Satellites have detected meteors entering Earth's atmosphere from above, providing a perspective impossible from the ground. These observations have helped calibrate models of meteor flux and have revealed details about the upper atmosphere's response to meteor activity. The prediction of meteor shower activity has become increasingly sophisticated. By modelling the orbital evolution of debris particles and tracking the locations of dense clumps within streams, scientists can now forecast shower intensity years or even decades in advance. These predictions are not perfect, as the structure of debris streams is complex and not fully mapped, but they have proven remarkably accurate for many showers. For observers, meteor showers offer accessible opportunities to connect with the cosmos. No telescope is needed, only dark skies, clear weather, and patience. The best strategy is to find a location away from city lights. Allow your eyes to adapt to the darkness for at least 20 minutes, and then simply watch the sky. Lying on a blanket or reclining in a lawn chair allows comfortable viewing of a large portion of the sky. While the radiant indicates the direction from which meteors will appear to come, meteors can appear anywhere in the sky, so a wide field of view is advantageous. The experience of watching a meteor shower is qualitatively different from ordinary stargazing. The stars are constant, predictable, unchanging on human timescales, but meteors are events, brief and unpredictable, demanding attention in the moment they occur. There is an element of anticipation, of waiting for something to happen, that gives meteor watching a unique character. And when a bright meteor does streak across the sky, there is a thrill of witnessing something fleeting and beautiful, a moment shared with the cosmos. Meteor showers also provide opportunities for citizen science. Organizations like the American Meteor Society and the International Meteor Organization coordinate observations from amateur astronomers around the world. By counting meteors and recording their characteristics, observers contribute to databases that help scientists understand shower activity and debris stream structure. This is one area of astronomy where amateur contributions remain genuinely valuable, as professional observatories cannot monitor the entire sky continuously. As we conclude this exploration of meteor showers, let us appreciate these annual celestial celebrations for what they are: regular reminders of our connection to the broader solar system. The debris that produces these displays was shed by comets that have orbited the Sun for thousands or millions of years. When we watch a meteor shower, we are seeing material that may have been part of a comet when dinosaurs walked the Earth, or even earlier. These particles have travelled immense distances and waited immense times for their moment of glory, their brief flash of light in our atmosphere. The predictability of meteor showers means that we can plan to observe them, can mark our calendars and arrange our schedules to be under dark skies at the right time. This regularity transforms meteor watching from a chance occurrence into an intentional act, a deliberate choice to step outside and connect with the cosmos. And in that choice, in that moment of looking up, we participate in a tradition as old as humanity itself. Chapter 7. Famous Meteors and Meteorite Falls. Throughout history, the annals of human history contain numerous accounts of spectacular meteor events, moments when the sky blazed with unexpected light and stones fell from the heavens. These events have shaped cultures, influenced beliefs, and advanced scientific understanding. From ancient times to the present day, famous meteors and meteorite falls have left their mark on human consciousness, reminding us of our vulnerability and our connection to the wider cosmos. Among the most celebrated meteorites in history is the Hoba meteorite of Namibia, the largest known meteorite on Earth. Discovered in 1920 by a farmer ploughing his field, the Hoba meteorite weighs approximately 60 metric tons and measures about 2.7 meters by 2.7 meters by 0.9 meters. Despite its enormous size, the meteorite created no obvious impact crater, suggesting that it may have slowed significantly during atmospheric entry due to its flat shape, which would have caused it to decelerate like a giant skipping stone. The Hoba meteorite is an ataxite, a rare type of iron meteorite with a very high nickel content. Its composition and structure indicate that it originated from the core of a differentiated asteroid, a body large enough to have separated into distinct layers of core, mantle, and crust. The meteorite has remained in place since its discovery and is now a national monument, visited by thousands of people each year who come to marvel at this massive visitor from space. The Namibian government declared it a protected site in 1955, ensuring that this remarkable object will remain undisturbed for future generations to appreciate. The surface of the Hoba meteorite bears the characteristic features of atmospheric entry, including regmaglypts, the thumbprint-like depressions created by ablation during the fiery descent through Earth's atmosphere. These features, combined with a thin fusion crust that has largely weathered away over the estimated 80,000 years since its fall, tell the story of its violent arrival. Yet the meteorite itself appears serene, a massive iron block resting peacefully in the African soil. Its journey of millions of years concluded in this quiet corner of the world. Another historically significant meteorite is the Willamette meteorite, the largest ever found in North America. Weighing approximately 15.5 metric tons, this iron meteorite was discovered in Oregon in 1902, though indigenous peoples of the region had known of its existence for centuries. The Clackamas people considered the meteorite sacred, calling it Tomanawas, and believing it had spiritual significance as a union of sky, earth, and water. They would dip their arrows in the rainwater that collected in the meteorite's distinctive cavities before hunts and battles. The Willamette meteorite's surface is marked by deep cavities and holes, giving it an almost sculptural appearance. These features were not created during atmospheric entry, but rather by terrestrial weathering over the thousands of years since its fall. The iron-nickel metal reacted with water and oxygen, creating iron oxides that were washed away, gradually enlarging the cavities. This weathering process reveals how even the most durable cosmic visitors are slowly transformed by Earth's environment. The meteorite's modern history is marked by controversy. After its discovery by a settler named Ellis Hughes, ownership disputes arose involving Hughes, the Oregon Iron and Steel Company, on whose land the meteorite was found, and later the Clackamas tribe, who sought its return as a sacred object. The meteorite eventually came to reside at the American Museum of Natural History in New York, where it remains one of the most popular exhibits. In 2000, the museum reached an agreement with the Confederated Tribes of Grand Ronde, descendants of the Clackamas, allowing for ceremonial access to the meteorite, while it remains on public display. The Ensisheim meteorite holds a special place in history as the oldest meteorite fall with a precisely recorded date. On November 7, 1492, just weeks after Columbus reached the Americas, a loud explosion was heard over the town of Ensisheim in Alsace, then part of the Holy Roman Empire. Witnesses saw a stone fall from the sky and embed itself in a wheat field. The stone, weighing approximately 127 kilograms, was recovered and became an object of intense curiosity and veneration. The Ensisheim fall occurred at a pivotal moment in European history, and it was interpreted through the lens of the era's beliefs. King Maximilian I, who happened to be in the region, declared the meteorite a sign from God, a good omen for his military campaigns. He ordered that the stone be preserved in the local church, where it remained for centuries. Pieces were gradually chipped away by visitors seeking souvenirs or talismans, reducing its mass to about 55 kilograms by the time it was moved to a museum. The Ensisheim meteorite is an ordinary chondrite, one of the most common types of stony meteorite. Its composition is similar to the primordial material from which the solar system formed, making it a sample of the early solar nebula preserved for 4.5 billion years. The fact that such a scientifically valuable object fell at a time when its true nature could not be understood adds a poignant dimension to its story. For centuries it was revered as a divine sign, its cosmic origins unsuspected. The Lagal meteorite fall of 1803 marked a turning point in scientific understanding. On April 26 of that year, a brilliant fireball was seen over Normandy, France, followed by loud detonations. Thousands of stones rained down over an area of several square kilometres near the town of Lagal. The fall was witnessed by numerous credible observers, and the physical evidence was overwhelming. The French Academy of Sciences dispatched Jean-Baptiste Biot, a young and talented physicist, to investigate. Biot conducted a thorough, systematic study, interviewing witnesses, mapping the distribution of fallen stones, and analysing the meteorites themselves. His report, presented to the Academy later that year, provided irrefutable evidence that stones did indeed fall from the sky. This conclusion, which had been resisted by many scientists despite centuries of eyewitness accounts, finally gained acceptance in the scientific community. The Lagal fall is considered the birth of meteoritics as a scientific discipline. Before Biot's investigation, the idea of rocks falling from space was widely dismissed by educated Europeans as superstition. Afterward, the reality of meteorites was established beyond reasonable doubt, and scientists began the work of understanding their nature and origins. The careful empirical approach that Biot brought to the investigation set a standard for future meteorite research. The Peekskill meteorite of 1992 achieved fame not for its size or scientific importance, but for the dramatic circumstances of its arrival. On October 9th, a bright fireball was observed over the eastern United States, travelling from Kentucky to New York. The event occurred on a Friday evening when many high school football games were in progress, and the fireball was captured on at least 16 different video recordings, making it one of the best documented meteor events in history. The meteorite's journey ended in Peekskill, New York, where a 12-kilogram fragment struck a parked Chevrolet Malibu owned by Michelle Knapp. The stone punched through the trunk of the car and came to rest in a shallow crater beneath the vehicle. The car, which Knapp had purchased just days earlier for $300, became famous in its own right. Both the meteorite and the damaged car have been displayed at museums and exhibitions around the world, and the car has sold for amounts far exceeding its original value. The Peekskill meteorite is an H6 ordinary chondrite a common type that provides limited scientific novelty. However, the extensive video documentation allowed scientists to calculate its pre-atmospheric orbit with unprecedented precision. The meteorite was determined to have originated from the Apollo asteroid population, objects whose orbits cross that of Earth. This orbital information, combined with the meteorite's composition, helps scientists understand the pathways by which material from the asteroid belt reaches Earth. The Chelyabinsk event of February 15, 2013 was the most significant meteor event of the modern era, demonstrating both the potential danger of cosmic impacts and the power of modern documentation technology. At approximately 9:20 local time, a small asteroid about 20 meters in diameter entered Earth's atmosphere over Russia at a shallow angle, traveling at roughly 19 kilometers per second. The resulting fireball was brighter than the sun, casting moving shadows even in the daylight. The object exploded at an altitude of about 30 kilometers, releasing energy equivalent to approximately 500 kilotons of TNT, roughly 30 times the energy of the atomic bomb dropped on Hiroshima. The explosion generated a powerful shockwave that damaged thousands of buildings in the city of Chelyabinsk and surrounding areas, injuring approximately 500 people, mostly from flying glass. The Chelyabinsk event was documented by hundreds of dashboard cameras, security cameras, and smartphone videos, providing scientists with an unprecedented wealth of data. These recordings allowed precise reconstruction of the object's trajectory, velocity, and breakup sequence. The footage also captured the human experience of the event, showing the brilliant flash of light, the long delay before the shockwave arrived, and the startled reactions of witnesses. Fragments of the Chelyabinsk meteorite were recovered from a wide area, with the largest piece, weighing about 654 kilograms, retrieved from the bottom of Lake Chebakul, where it had punched through the ice. The meteorite is an LL5 ordinary chondrite, and its study has provided insights into the internal structure and strength of small asteroids. The event also prompted renewed attention to planetary defense, highlighting the need for better detection and tracking of near-Earth objects. The Allende meteorite, which fell in Mexico on February 8, 1969, is considered one of the most important meteorites ever recovered, not because of spectacular circumstances, but because of its scientific value. The fall occurred just months before the Apollo 11 moon landing, and the meteorites provided scientists with pristine extraterrestrial material to study at a time when techniques for analyzing such samples were being refined. Allende is a carbonaceous chondrite, a type of meteorite that contains some of the most primitive material in the solar system. Within its dark matrix are calcium-aluminum-rich inclusions, or Ki, which are believed to be among the first solid materials to have formed in the solar nebula. These inclusions have been dated to 4.567 billion years ago, providing the most precise age for the solar system itself. The Allende meteorite also contains pre-solar grains, tiny particles that formed in the atmospheres of dying stars before the solar system existed. These grains survived the formation of the solar nebula and were incorporated into the meteorite's parent body, where they remained preserved for billions of years. By analyzing these pre-solar grains, scientists can study the nuclear processes that occurred in stars that died before our sun was born. The Murchison meteorite, which fell in Australia on September 28, 1969, is another carbonaceous chondrite of immense scientific importance. Like Allende, Murchison contains primitive material from the early solar system, but it is particularly notable for its organic content. Analysis of the Murchison meteorite has revealed over 90 different amino acids, the building blocks of proteins, as well as nucleobases, sugars, and other organic compounds. The presence of these organic molecules in a meteorite has profound implications for the origin of life on Earth. It demonstrates that the chemical precursors of life can form in space without the involvement of living organisms. Some scientists have proposed that meteorites like Murchison may have delivered organic compounds to the early Earth, providing raw materials for the emergence of life. While this hypothesis remains debated, the Murchison meteorite has become a cornerstone of astrobiological research. The Sikhote-Alin meteorite fall of February 12, 1947, was one of the largest witnessed meteorite falls in modern history. At about 10:38 local time, a brilliant fireball appeared over the Sikhote-Alin mountains in eastern Siberia. The object fragmented during its descent, producing a shower of iron meteorites that created over 100 small craters, the largest about 26 meters in diameter. The fall was witnessed by numerous people and was famously depicted in a painting by artist P.I. Medvedev, who happened to be looking out his window at the moment of the fireball's appearance. His painting, showing the bright trail against a winter sky, has become one of the most iconic images in meteoritics. Expeditions to the fall site recovered approximately 23 metric tons of meteoritic material, making Sikhote-Alin one of the largest meteorite recoveries ever. The Sikhote-Alin meteorite is classified as an iron meteorite of the IIAB group. Many specimens display distinctive shapes, either smooth and sculpted by atmospheric ablation or jagged and fragmented from breakup during flight. The variety of forms provides a natural laboratory for studying the processes that affect meteoroids during atmospheric entry. The Tunguska event of June 30, 1908 remains one of the most mysterious and powerful cosmic impacts in recorded history, despite the fact that no meteorite was ever recovered. At approximately 7:17 local time, an enormous explosion occurred over the remote Tunguska region of Siberia, flattening an estimated 80 million trees over an area of 250 square kilometers. The explosion is estimated to have released energy equivalent to 10 to 15 megatons of TNT, roughly 1,000 times more powerful than the atomic bomb dropped on Hiroshima. The blast waves circled the globe, and the dust raised by the explosion caused unusually bright night skies over Europe and Asia for several days afterward. Yet despite the enormous energy release, no impact crater was found, and no significant meteorite fragments have ever been recovered from the site. The most widely accepted explanation is that the Tunguska object was a small asteroid or comet fragment, perhaps 50 to 60 meters in diameter, that exploded in the atmosphere at an altitude of 5 to 10 kilometers. The airburst released all of the object's kinetic energy into the atmosphere, creating the devastating blast wave without leaving a crater. The lack of recovered material may indicate that the object was composed of relatively fragile material that was completely vaporized in the explosion. The Tunguska event serves as a sobering reminder of the potential consequences of cosmic impacts. Had the object arrived a few hours later, Earth's rotation would have placed a major city beneath its path. The event has motivated much of the modern effort to detect and track near-Earth objects, with the goal of providing warning of potential impacts and eventually the capability to deflect threatening objects. The Nakhla meteorite, which fell in Egypt on June 28, 1911, is famous for being one of the first meteorites identified as originating from Mars. According to local accounts, the fall was witnessed by farmers, and one stone allegedly struck and killed a dog, which would make it the only known case of a meteorite killing an animal, though this claim has never been verified. Nakhla is a nachlite, a type of Martian meteorite composed primarily of the mineral augite. The meteorites were blasted off the surface of Mars by a large impact approximately 11 million years ago and wandered through space until they encountered Earth. Analysis of trapped gases within the meteorite matches the composition of Mars's atmosphere as measured by spacecraft, confirming its Martian origin. The study of Martian meteorites like nebula has provided valuable information about the geology and history of Mars, complementing data from robotic missions. These meteorites represent the only samples of Mars currently available for laboratory analysis, making them invaluable to planetary scientists. The eventual return of samples by future missions will allow comparison with these natural deliveries. The Allen Hills 84001 meteorite, discovered in Antarctica in 1984, became the center of one of the most controversial scientific announcements of the 20th century. In 1996, a team of NASA scientists announced that the meteorite, another Martian sample, contained possible evidence of ancient microbial life. The evidence included microscopic structures that resembled bacteria, mineral formations consistent with biological activity, and organic molecules. The announcement generated worldwide attention and sparked intense scientific debate. Subsequent research has cast doubt on the biological interpretation, with most scientists now concluding that the features can be explained by non-biological processes. However, the controversy stimulated renewed interest in astrobiology and the search for life beyond Earth. It also highlighted the importance of meteorites as potential carriers of information about conditions on other worlds. The Fukang meteorite, discovered in China in 2000, is celebrated not for its scientific importance, but for its extraordinary beauty. This palisite, a type of stony iron meteorite, contains large olivine crystals embedded in a matrix of iron-nickel metal. When sliced thin and backlit, the golden-green olivine crystals glow like stained glass windows, creating one of the most visually stunning natural objects on Earth. Palisites are thought to form at the boundary between the iron core and rocky mantle of differentiated asteroids. The olivine crystals crystallized from magma deep within the asteroid, while the metal represents material from the core. The collision that shattered the parent asteroid mixed these materials together, creating the distinctive palisite structure. Fukang specimens have sold for high prices to collectors, and large slices have been displayed in museums around the world. The Campo del Cielo meteorites of Argentina represent one of the largest known strewn fields on Earth. The name, meaning field of heaven in Spanish, reflects the indigenous Mocovi people's belief that the irons had fallen from the sky, a belief that predates European contact. Spanish explorers first reported the meteorites in 1576, making Campo del Cielo one of the earliest recorded meteorite localities in the Americas. The strewn field extends over an area of approximately 60 square kilometres and contains numerous craters, the largest about 100 metres in diameter. Thousands of individual meteorite specimens have been recovered, with the largest single mass weighing approximately 37 metric tons. The meteorites are coarse octahedrites, iron meteorites with a distinctive crystalline structure that becomes visible when the metal is etched with acid. The history of Campo del Cielo illustrates the long relationship between humans and meteorites. Indigenous peoples knew of the irons for centuries before Europeans arrived, and some evidence suggests they may have used meteoritic iron for tools. The site has been studied by scientists since the 19th century and continues to yield new specimens and insights. The Gibeon meteorites of Namibia represent another significant iron meteorite-strewn field. The meteorites were known to indigenous San people who used the metal for tools and weapons. The first scientific description came in 1836, and since then, thousands of specimens totaling over 25 metric tons have been recovered. Gibeon meteorites are fine octahedrites displaying a beautiful Widmanstätten pattern when etched. This pattern, consisting of interlocking plates of two iron-nickel alloys, called kamacite and taenite, can only form through extremely slow cooling, on the order of a few degrees per million years. Such slow cooling could only occur deep within an asteroid, where the surrounding rock provided insulation. The Widmanstätten pattern is thus a signature of the meteorite's origin in the core of a differentiated asteroid. These famous meteorites and meteor events span centuries and continents, yet they share common threads. Each represents a connection between Earth and the wider cosmos, a physical link to objects and processes far beyond our everyday experience. Each has contributed to human knowledge, whether by advancing scientific understanding, inspiring cultural traditions, or simply reminding us of the dynamic nature of our solar system. As we reflect on these remarkable events, we are reminded that the sky is not merely a backdrop for human affairs, but an active participant in our planet's story. Stones do fall from the heavens, carrying messages from the deep past and distant places. The history of meteorite falls is, in a sense, the history of the universe making contact with Earth, one fragment at a time. Chapter 8. Impact Craters. Scars on Earth's Surface. The Earth bears witness to a violent cosmic history, its surface marked by the scars of countless impacts over billions of years. These impact craters, ranging from small depressions to vast circular structures hundreds of kilometers across, tell the story of a solar system where collisions are not rare accidents, but fundamental processes that have shaped worlds. Understanding impact craters reveals not only the history of our planet, but also the ongoing relationship between Earth and the population of asteroids and comets that share our cosmic neighbourhood. Unlike the Moon, whose ancient surface preserves a detailed record of bombardment stretching back over 4 billion years, Earth's crater record is fragmentary and incomplete. Our planet's active geology, with its plate tectonics, volcanism, erosion, and sedimentation, continuously erases the evidence of past impacts. Craters that formed hundreds of millions of years ago have been worn away, buried, or deformed beyond recognition. Only the youngest and largest craters remain clearly visible, while others must be detected through subtle geological clues. Despite these challenges, scientists have identified nearly 200 confirmed impact structures on Earth, with more candidates awaiting verification. These structures range from small simple craters just a few tens of meters across to enormous complex structures exceeding 200 kilometers in diameter. Each crater tells a story of a moment when the ordinary flow of geological time was interrupted by an extraordinary event, a collision that released more energy in seconds than all the world's nuclear weapons combined. The Barringer crater in Arizona, also known as Meteor crater, is perhaps the most famous impact structure on Earth, and certainly the best preserved of its size. Measuring approximately 1.2 kilometers in diameter and 170 meters deep, this bowl-shaped depression was created approximately 50,000 years ago when an iron meteorite about 50 meters in diameter struck the desert at a velocity of roughly 12 kilometers per second. The impact released energy equivalent to about 10 megatons of TNT, vaporizing most of the impactor and excavating approximately 300 million metric tons of rock. The resulting crater has been preserved by the arid Arizona climate, which minimizes erosion. The rim of the crater still rises about 45 meters above the surrounding plain, and large blocks of limestone ejected during the impact litter the area around the structure. Barringer crater played a crucial role in establishing the importance of impact processes in shaping planetary surfaces. In the early 20th century, mining engineer Daniel Barringer became convinced that the crater was formed by a meteorite impact and spent years searching for the main mass of the impactor, which he believed lay buried beneath the crater floor. Although his search was unsuccessful, as we now know the impactor was largely vaporized, his work helped establish the impact origin of the crater against competing volcanic hypotheses. The crater has since become a natural laboratory for studying impact processes. Scientists have used it to develop and test models of crater formation, to study the effects of impacts on target rocks, and to train astronauts preparing for lunar missions. The well-preserved structure allows detailed examination of features that are obscured or erased at older craters, making it invaluable for understanding impact mechanics. The Chicxulub crater, buried beneath the Yucatan Peninsula of Mexico, is far larger than Barringer and far more consequential for life on Earth. This structure, approximately 180 kilometers in diameter, was formed 66 million years ago by an asteroid estimated at 10 to 15 kilometers in diameter. The impact released energy equivalent to billions of nuclear weapons and triggered a global catastrophe that ended the age of dinosaurs. The Chicxulub crater was not discovered until the late 20th century, despite its enormous size. The structure is buried beneath hundreds of meters of sediment and is not visible at the surface. Its existence was first suspected in the late 1970s when geophysicists conducting oil exploration surveys noticed unusual patterns in gravity and magnetic data. Subsequent drilling and analysis confirmed that these anomalies marked a massive impact structure. The impact that created Chicxulub was one of the most significant events in the history of life on Earth. The immediate effects included a blast wave that devastated everything within hundreds of kilometers, tsunamis that swept across the Gulf of Mexico and beyond, and wildfires ignited by the rain of superheated debris falling back from the impact plume. But the long-term effects were even more devastating. The impact ejected vast quantities of dust and aerosols into the atmosphere, blocking sunlight and causing global temperatures to plummet. Sulfur released from the target rocks combined with water to form sulfuric acid, which fell as acid rain. The darkness and cold persisted for months or years, causing the collapse of photosynthesis-based food chains. Approximately 75% of all species on Earth went extinct, including all non-avian dinosaurs. The discovery of Chicxulub and its link to the mass extinction was one of the great scientific detective stories of the 20th century. In 1980, physicist Luis Alvarez and his geologist son Walter proposed that the extinction was caused by an asteroid impact, based on their discovery of a thin layer of clay enriched in iridium, an element rare on Earth but common in asteroids, at the geological boundary marking the extinction. This hypothesis was initially controversial, but gained acceptance as evidence accumulated, culminating in the identification of the Chicxulub crater as the smoking gun. The Vredefort crater in South Africa is the largest confirmed impact structure on Earth, with an estimated original diameter of 250 to 300 kilometers. The structure formed approximately 2 billion years ago, making it also one of the oldest well-preserved impact sites. Erosion over 2 billion years has removed much of the original crater, but the central uplift and surrounding ring structures remain visible, creating a distinctive geological feature known as the Vredefort Dome. The Vredefort impact was caused by an asteroid estimated at 10 to 15 kilometers in diameter, similar in size to the Chicxulub impactor. The energy released would have been catastrophic on a global scale, though the effects on life at that time are difficult to assess because the fossil record from 2 billion years ago is sparse. The impact may have influenced the evolution of early life, but any such effects remain speculative. The Vredefort structure has been designated a UNESCO World Heritage Site, recognized for its scientific importance in understanding impact processes and early Earth history. The exposed rocks provide a cross-section through a large impact structure, allowing geologists to study features that are buried or erased at other sites. The dome has also become a popular destination for geological tourism, attracting visitors who wish to walk on the floor of an ancient cosmic collision. The Sudbury Basin in Ontario, Canada, is another ancient giant, formed approximately 1.85 billion years ago. The original crater is estimated to have been 200 to 250 kilometers in diameter, though subsequent geological processes have deformed the structure into an elliptical shape, measuring roughly 60 by 30 kilometers. Despite this deformation, the Sudbury Basin remains one of the best studied impact structures on Earth. The Sudbury impact has economic as well as scientific significance. The collision created conditions that concentrated valuable metals, including nickel, copper, and platinum group elements, in deposits that have been mined for over a century. The Sudbury Mining District is one of the world's largest sources of nickel, and the economic activity it supports has made the impact crater a source of prosperity for the region. The relationship between the impact and the ore deposits is complex and not fully understood. Some researchers believe the metals were derived from the impactor itself, which may have been an iron-nickel asteroid. Others suggest that the impact mobilized metals already present in Earth's crust, concentrating them through processes triggered by the collision. Whatever the mechanism, the Sudbury Basin demonstrates that cosmic violence can create valuable resources. The Popogai crater in Siberia, approximately 100 kilometers in diameter, formed about 35 million years ago. The impact occurred in rocks rich in carbon, and the extreme pressures generated during the collision converted some of this carbon into diamonds. These impact diamonds are generally small and of industrial rather than gem quality, but they represent an unusual byproduct of cosmic violence. The Popogai diamonds were kept secret by the Soviet government for decades, as their existence was considered strategically sensitive. The deposit is estimated to contain trillions of carats of diamonds, far exceeding all other known diamond reserves combined. However, the remote location and the diamond's industrial quality have limited commercial development. The Ries crater in Germany, approximately 24 kilometers in diameter, formed about 15 million years ago. The crater is notable for its excellent preservation, and for the nearby Steinheim crater, which formed at the same time and may have been created by a binary asteroid or by fragments of a single asteroid that broke apart before impact. The Ries crater has been extensively studied and has contributed significantly to our understanding of impact processes. The town of Nördlingen, located within the crater, is built largely of swevite, a type of rock formed by the impact that contains shocked minerals and glass. The local church, St. George's Church, contains an estimated 72,000 metric tons of swevite in its walls, making it perhaps the largest structure built from impact-generated rock. The Manicouagan crater in Quebec, Canada, is one of the most visually striking impact structures when viewed from space. The 100-kilometer diameter crater, formed approximately 214 million years ago, now contains an annular lake that freezes in winter, creating a distinctive ring of ice, visible in satellite images. The lake fills a ring-shaped depression between the central uplift and the outer rim, a common feature of large complex craters. The Manicouagan impact has been proposed as a possible cause of a minor extinction event at the end of the Triassic period, though the timing does not precisely match the extinction boundary. The crater has also been suggested as part of a chain of impacts that may have occurred within a short geological time span, possibly caused by the breakup of a large asteroid. This hypothesis remains debated, but it highlights the possibility that multiple impacts can occur in rapid succession. The Chesapeake Bay impact structure, located beneath the bay and surrounding areas of Virginia and Maryland, is one of the largest impact craters in the United States. The structure, approximately 85 kilometers in diameter, formed about 35 million years ago when an asteroid struck what was then a shallow sea. The impact created a complex crater that was subsequently buried by sediments, hiding its existence until geophysical surveys in the 1990s revealed its presence. The Chesapeake Bay impact has had lasting effects on the region's geology and hydrology. The crater disrupted the local groundwater system, creating conditions that persist to the present day. Water quality in wells drilled into the crater differs from that in surrounding areas, and the buried structure influences the flow of underground water. The impact thus continues to affect human activities millions of years after it occurred. The Wolf Creek crater in Western Australia, approximately 880 metres in diameter, is one of the best preserved small craters on Earth. The structure formed less than 300,000 years ago, possibly much more recently, and remains clearly visible in the arid landscape. The crater is sacred to the local Jaru people, who call it Kandamalal and associate it with a rainbow serpent that emerged from the ground. Fragments of the iron meteorite that created Wolf Creek crater have been found in the surrounding area, providing direct evidence of the impactor's composition. The crater has become a popular tourist destination, attracting visitors who wish to stand inside a structure created by cosmic violence. The site's remote location has helped preserve it from the development that has obscured or destroyed many other craters. The study of impact craters extends beyond Earth to other bodies in the solar system. The Moon's surface is saturated with craters, preserving a record of bombardment that extends back over 4 billion years. Mars, Mercury, and the moons of the outer planets also bear extensive crater populations. By studying craters on these bodies, scientists can learn about the history of impacts throughout the solar system and can calibrate the rate at which craters form. The comparison of crater populations on different worlds has revealed that the inner solar system experienced a period of intense bombardment early in its history, known as the Late Heavy Bombardment. During this period, approximately 3.8 to 4.1 billion years ago, the rate of impacts was far higher than today, possibly due to gravitational disturbances that scattered asteroids and comets into the inner solar system. The Late Heavy Bombardment would have been catastrophic for any life that might have existed on Earth at the time, though some researchers have suggested that life may have survived in protected environments. The formation of an impact crater is a complex process that unfolds in distinct stages. The first stage, contact and compression, begins when the impactor strikes the target surface. The kinetic energy of the impactor is converted into shock waves that propagate through both the impactor and the target rock. Pressures at the point of impact can exceed millions of atmospheres, far exceeding the strength of any known material. The second stage, excavation, involves the outward and upward movement of target material driven by the shock wave. A bowl-shaped cavity called the transient crater is excavated as material is ejected from the impact site. Some of this ejected material falls back into the crater, while the rest is deposited around the rim as an ejector blanket. The transient crater is typically deeper and smaller than the final crater. The third stage, modification, involves the collapse and adjustment of the transient crater. In small craters, this modification is minimal, resulting in simple bowl-shaped structures. In larger craters, the walls of the transient crater collapse inward, and the floor may rebound upward, creating complex structures with central peaks, peak rings, and terraced walls. The largest impacts can create multi-ring basins, enormous structures, with multiple concentric rings of mountains. The energy released during a large impact is almost incomprehensible. The Chicxulub impact released approximately 100 trillion tons of TNT equivalent, more energy than has been released by all the earthquakes and volcanic eruptions in human history combined. This energy is sufficient to vaporize the impactor and a significant volume of target rock, to melt and shock a much larger volume, and to eject material that can travel hundreds or thousands of kilometers from the impact site. The environmental effects of large impacts extend far beyond the immediate crater. Dust and aerosols injected into the atmosphere can block sunlight, causing global cooling. Nitrogen oxides formed by the shock-heated atmosphere can destroy the ozone layer, allowing harmful ultraviolet radiation to reach the surface. Wildfires, triggered by the thermal radiation from the impact fireball and by the re-entry of hot ejecta, can consume vast areas of vegetation. Tsunamis generated by oceanic impacts can devastate coastlines thousands of kilometers from the impact site. The recognition of these effects has transformed our understanding of Earth history. Mass extinctions that were once attributed to gradual environmental changes are now recognized as potentially linked to impact events. The Chicxulub impact and the end Cretaceous extinction are the best established example, but other extinctions may also have impact connections. The search for impact signatures at extinction boundaries has become an active area of research. The ongoing threat of impacts has also gained recognition. While large impacts are rare on human timescales, they are inevitable over geological time. The Chelyabinsk event of 2013 demonstrated that even relatively small objects can cause significant damage and injuries. Larger objects capable of regional or global devastation exist in the near-Earth population and will eventually strike our planet unless they are detected and deflected. As we contemplate the impact craters that scar Earth's surface, we are reminded of our planet's place in a dynamic and sometimes violent solar system. The same processes that delivered water and organic compounds to the early Earth, enabling the emergence of life, also have the potential to destroy that life in an instant. The craters are monuments to this duality, reminders that the cosmos is both creator and destroyer. Yet there is also beauty in these scars. The ring lake of Manicouagan, the rolling hills of the Vredefort Dome, the stark bowl of Barringer Crater, each has its own austere grandeur. These are places where the ordinary rules of geology were suspended, where energies beyond human experience reshaped the land in moments. To visit a crater is to stand at a place where the sky touched the earth, where the cosmic and the terrestrial became one. Chapter 9. Meteorite Types and What They Tell Us. When a meteoroid survives its fiery passage through Earth's atmosphere and comes to rest on our planet's surface, it becomes a meteorite, a tangible sample of material from beyond our world. These cosmic visitors come in a remarkable variety of types, each carrying different information about the conditions and processes that shaped our solar system. By studying meteorites, scientists have learned more about the early solar system than could ever be gleaned from Earth-bound observations alone. These rocks are messengers from the past, archives of information waiting to be decoded. The classification of meteorites has evolved considerably since the early days of meteoritics, becoming increasingly sophisticated as analytical techniques have improved. Today, meteorites are divided into three broad categories based on their composition: stony meteorites, iron meteorites, and stony iron meteorites. Within each category, numerous subgroups and classes reflect the diverse origins and histories of these cosmic samples. Understanding this classification system is essential for appreciating what meteorites can tell us about the solar system's past. Stony meteorites are by far the most common type, accounting for approximately 94% of all observed falls. Despite their prevalence among falls, stony meteorites are underrepresented in collections because they resemble terrestrial rocks and are easily overlooked. An iron meteorite lying in a field will attract attention, but a stony meteorite might be dismissed as just another rock. This observational bias means that the true proportion of stony meteorites among all meteorites reaching Earth is even higher than the full statistics suggest. Stony meteorites are further divided into two major groups, chondrites and achondrites. This division reflects a fundamental difference in the histories of these rocks. Chondrites are primitive, meaning they have remained largely unchanged since they formed in the early solar system. Achondrites, in contrast, have been processed by melting and differentiation, losing the primitive characteristics that make chondrites so valuable for understanding solar system origins. Chondrites take their name from chondrules, small spherical structures, typically 1 millimeter or less in diameter, that are found embedded in the meteorite matrix. These tiny spheres are among the oldest solid materials in the solar system, having formed approximately 4,567 billion years ago in the solar nebula, the cloud of gas and dust from which the sun and planets formed. Chondrules appear to have been molten droplets that cooled and solidified while floating freely in space, though the exact mechanism that melted them remains debated. The presence of chondrules is what distinguishes chondrites from all other types of meteorites. No terrestrial rock contains these structures, and no process on Earth can create them. When you hold a chondrite in your hand, you are holding material that has remained essentially unchanged since before the planets existed. The chondrules within it are older than Earth, older than the Moon, older than any rock you could find on our planet's surface. Chondrites are subdivided into several classes based on their chemical composition and the degree to which they have been altered by heat and water. The major classes include ordinary chondrites, carbonaceous chondrites, and enstatite chondrites, each representing material from different regions or conditions in the early solar system. Ordinary chondrites are the most common type of meteorite, accounting for about 80% of all falls. They are called ordinary, not because they are uninteresting, but because they are so frequently encountered. Ordinary chondrites are further divided into three groups, designated H, L, and LL, based on their iron content. H chondrites have high iron content, L chondrites have low iron content, and LL chondrites have low iron and low metal content. Despite their abundance, ordinary chondrites present a puzzle. Their composition does not match any known asteroid type observed through telescopes. This mismatch, sometimes called the ordinary chondrite paradox, suggests that the surfaces of asteroids may be altered by space weathering in ways that change their spectral properties. Alternatively, ordinary chondrites may come from a relatively small number of asteroids that happen to be efficient at delivering material to Earth. Carbonaceous chondrites are rarer than ordinary chondrites but scientifically invaluable. These dark, often fragile meteorites contain significant amounts of carbon, including organic compounds such as amino acids, the building blocks of proteins. Some carbonaceous chondrites also contain water, locked within hydrated minerals that formed when liquid water flowed through the parent asteroid billions of years ago. The organic compounds in carbonaceous chondrites are not evidence of life, but rather demonstrate that complex chemistry can occur in space without biological involvement. The amino acids found in these meteorites include both types used by terrestrial life and types not found in living organisms, indicating an abiotic origin. Nevertheless, the presence of these compounds has profound implications for the origin of life on Earth. Meteorites may have delivered organic building blocks to the early Earth, providing raw materials for the emergence of life. Carbonaceous chondrites are divided into several groups, each named after a representative meteorite. The Ci group, named after the Ivuna meteorite, represents the most primitive material known, with a composition that closely matches the Sun's photosphere for non-volatile elements. Ci chondrites are essentially samples of the original solar nebula preserved for 4.5 billion years. They are extremely rare and extremely valuable for scientific research. The Cm group, named after the Murchison meteorite, is perhaps the most studied class of carbonaceous chondrites. Murchison, which fell in Australia in 1969, has yielded an astonishing array of organic compounds, including over 90 different amino acids. The meteorite has been analysed by countless researchers using every available technique, and it continues to reveal new secrets decades after its fall. The CV group, named after the Vigorano meteorite, includes the famous Allende meteorite. CV chondrites contain large, well-defined chondrules and abundant calcium-aluminum-rich inclusions, or CAIs. These CAIs are the oldest dated solids in the solar system, providing the benchmark age of 4.567 billion years for the solar system's formation. Enstatita chondrites are a smaller group characterized by their highly reduced chemistry, meaning they formed under conditions with very little oxygen. The minerals in enstatite chondrites include some that are unstable in the presence of oxygen and water, indicating formation in a region of the solar nebula that was unusually dry and chemically reducing. Some researchers have proposed that enstatite chondrites formed close to the Sun, where temperatures were high enough to drive off volatile elements. The oxygen isotope ratios in enstatite chondrites are similar to those of Earth, leading some scientists to suggest that these meteorites may represent the type of material from which our planet formed. This hypothesis remains controversial, but it illustrates how meteorite studies can inform our understanding of planetary formation. Achondrites are stony meteorites that lack chondrules, having been heated to the point where these primitive structures were destroyed. Most achondrites come from asteroids that experienced melting and differentiation, the process by which a body separates into layers of different composition, with dense metals sinking to form a core and lighter silicates rising to form a mantle and crust. The most common achondrites are the head meteorites, a group that includes howardites, eucrites, and diogenites. These meteorites are believed to come from the asteroid 4 Vesta, the second largest object in the asteroid belt. Spectroscopic observations of Vesta's surface match the composition of head meteorites, and the asteroid bears a large impact crater that could have ejected the material that eventually reached Earth. Eucrites are basaltic rocks, similar in some ways to the volcanic rocks found on Earth's ocean floors. They represent lava that erupted onto Vesta's surface early in the asteroid's history, when it was still hot enough to sustain volcanic activity. Diogenites are plutonic rocks that crystallize slowly beneath Vesta's surface, forming coarse-grained textures. Howardites are breccias, rocks composed of fragments of both eucrites and diogenites, mixed together by impacts on Vesta's surface. The HED meteorites provide a detailed picture of Vesta's geology, allowing scientists to study an asteroid's interior without sending a spacecraft to collect samples. The Dawn mission, which orbited Vesta from 2011 to 2012, confirmed many of the conclusions drawn from meteorite studies and added new details about the asteroid's structure and history. Lunar meteorites are achondrites that originated on the Moon. When large impacts occur on the lunar surface, they can eject material with enough velocity to escape the Moon's gravity. Some of this ejected material eventually finds its way to Earth, where it falls as meteorites. Lunar meteorites can be identified by their composition, which matches samples returned by the Apollo missions. More than 100 lunar meteorites have been identified, representing a diverse sampling of the Moon's surface. Some are basalts from the dark Maria, the ancient lava plains visible from Earth. Others are breccias from the bright highlands, composed of fragments of the moon's ancient crust. Lunar meteorites have been found on every continent and provide samples of regions not visited by Apollo astronauts, expanding our knowledge of lunar geology. Martian meteorites are even rarer than lunar meteorites, with only about 200 specimens known. These rocks were blasted off the surface of Mars by large impacts and wandered through space for millions of years before encountering Earth. Martian meteorites can be identified by the composition of gases trapped within them, which matches the Martian atmosphere as measured by spacecraft. Martian meteorites come in several types, reflecting the diversity of Martian geology. Schagotites are basaltic rocks, similar to volcanic rocks on Earth. Naklites are clinopyroxenites, igneous rocks composed primarily of the mineral augite. Chasinites are dunites, composed almost entirely of the mineral olivine. A fourth type, the orthopyroxenite Allan Hills 84-1, is unique and famous for the controversial claim that it contains evidence of ancient Martian life. The study of Martian meteorites has provided valuable information about Mars's geology, atmosphere, and history. These rocks represent the only samples of Mars currently available for laboratory analysis, making them precious resources for planetary science. Future sample return missions will eventually bring back rocks selected by scientists. But until then, Martian meteorites remain our primary source of Martian material. Iron meteorites, though less common than stony meteorites, are more likely to be recognized and collected because of their distinctive appearance. These dense metallic objects are composed primarily of iron and nickel, with smaller amounts of other elements. They represent the cores of differentiated asteroids, bodies that melted and separated into layers early in solar system history. When a differentiated asteroid is shattered by a collision, its core is exposed and fragmented. These core fragments become the iron meteoroids that eventually fall to Earth as iron meteorites. The journey from asteroid core to Earth's surface may take millions of years, during which the meteoroid is exposed to cosmic rays that leave detectable traces in the metal. Iron meteorites are classified based on their chemical composition and structure. The chemical classification uses Roman numerals and letters to designate groups with similar trace element patterns, such as IAB, TIAB, and IVA. These groups are thought to represent the cores of different parent asteroids, each with its own unique composition. The structural classification is based on the appearance of the meteorite when it is cut, polished, and etched with acid. This treatment reveals the Widmanstätten pattern, a distinctive arrangement of interlocking crystals that forms only through extremely slow cooling. The pattern consists of plates of kamacite, an iron-nickel alloy with low nickel content, bordered by taenite, an alloy with higher nickel content. The Widmanstätten pattern is one of the most beautiful features in all of nature, a geometric design that could only form in the heart of an asteroid. The pattern develops because kamacite and taenite have different crystal structures and different nickel contents. As the molten metal cools, kamacite crystals nucleate and grow along specific crystallographic planes, creating the characteristic crisscrossing pattern. The size of the kamacite plates in the Widmanstätten pattern depends on the cooling rate. Larger plates indicate slower cooling, while smaller plates indicate faster cooling. By measuring the plate's size, scientists can estimate how quickly the parent asteroid's core cooled, which in turn provides information about the size of the asteroid. Typical cooling rates are on the order of a few degrees per million years, implying parent bodies tens to hundreds of kilometers in diameter. Hexahedrites are iron meteorites with very low nickel content, below about 6%. At this composition, the metal consists entirely of kamacite, and no Riemann-Stetten pattern develops. Instead, hexahedrites display Neumann lines, fine parallel lines caused by shock deformation, probably from impacts on the parent asteroid. Octahedrites are the most common type of iron meteorite, with nickel contents between about 6 and 16%. These meteorites display the classic Riemann-Stetten pattern, with kamacite plates arranged in an octahedral geometry. Octahedrites are further subdivided based on the width of the kamacite plates, from coarsest to finest. Ataxites are iron meteorites with very high nickel content, above about 16%. At this composition, the metal consists primarily of taenite, and no Riemann-Stetten pattern develops. Ataxites are relatively rare and include some of the largest known meteorites, such as the Hoba meteorite of Namibia. Stony iron meteorites are the rarest of the three main categories, accounting for only about 1% of falls. These meteorites contain roughly equal proportions of silicate minerals and iron-nickel metal, representing material from the boundary regions of differentiated asteroids. The two main types of stony iron meteorites are pallasites and mesosidereites. Pallasites are among the most beautiful of all meteorites, consisting of olivine crystals embedded in a matrix of iron-nickel metal. When sliced thin and backlit, the golden-green olivine crystals glow with an inner light, creating a stunning visual effect. Pallasites are thought to form at the core mantle boundary of differentiated asteroids, where metal from the core mixed with silicates from the mantle. The formation of pallasites is not fully understood. One hypothesis suggests that they formed when the liquid metal core of an asteroid intruded into the overlying silicate mantle. Another hypothesis proposes that pallasites formed when impacts mixed core and mantle material together. Recent research has suggested that some pallasites may have formed in a more complex process involving multiple generations of melting and mixing. Mesosidereites are a more chaotic mixture of metal and silicates, lacking the orderly structure of pallasites. These meteorites appear to have formed through violent collisions that mixed material from different parts of one or more asteroids. The silicate portions of mesosidereites include both basaltic and plutonic rock types, suggesting a complex history of melting, crystallization, and impact mixing. Beyond these major categories, several unusual meteorite types deserve mention. Eurilites are a type of achondrite with an unusual composition, containing both olivine and pyroxene, along with carbon in the form of graphite and diamond. The diamonds in Eurilites are thought to have formed either by shock during impacts or by chemical vapor deposition in the solar nebula. Angrites are a rare type of achondrite with a distinctive composition rich in calcium and aluminum. These meteorites crystallized very early in solar system history, within a few million years of the formation of CAIs. Angrites provide important constraints on the timing of planetary differentiation and the distribution of radioactive elements in the early solar system. Aubrites are enstatite achondrites, meteorites that formed from the same highly reduced material as enstatite chondrites, but experienced melting and differentiation. Aubrites are almost entirely composed of the mineral enstatite, a magnesium silicate, and contain unusual minerals that are unstable in the presence of oxygen. The study of meteorites has revolutionized our understanding of the solar system. Before meteorites were recognized as extraterrestrial, scientists had no direct samples of material from beyond Earth. The moon was a distant light in the sky, the planets were points of light, and the asteroids were unknown. Meteorites opened a window into the cosmos, providing tangible evidence of worlds and processes far beyond human experience. Today, meteorites continue to yield new discoveries. Advanced analytical techniques allow scientists to measure isotopic ratios with unprecedented precision, revealing details of nuclear synthesis in ancient stars. Microscopic analysis reveals pre-solar grains, tiny particles that formed before the solar system existed and were incorporated into meteorite parent bodies. Organic chemistry identifies complex molecules that may have played roles in the origin of life. Each meteorite is a unique document, a record of conditions and events that occurred billions of years ago and millions of miles away. The information encoded in these rocks is patient, waiting for scientists with the right questions and the right tools to decode it. As our analytical capabilities improve, meteorites that have been in collections for decades continue to reveal new secrets. For those who collect or simply appreciate meteorites, there is a profound satisfaction in holding a piece of another world. The weight of an iron meteorite in your hand is the weight of an asteroid's core. The fusion crust on a stony meteorite is the record of its fiery arrival. The chondrules in a chondrite are older than any mountain, any ocean, any living thing on Earth. In these small objects, the vastness of space and time becomes tangible, something you can touch and hold and wonder at. Chapter 10. Hunting for Space Rocks. Meteorite Recovery. The search for meteorites is a pursuit that combines scientific rigour with the thrill of treasure hunting. Around the world, dedicated individuals and teams venture into deserts, ice fields, and ordinary landscapes in search of these cosmic visitors. Some are professional scientists conducting systematic surveys. Others are amateur enthusiasts driven by curiosity and the hope of discovery. Together, they have built collections that form the foundation of meteoritical research, providing the samples that scientists analyze to unlock the secrets of the solar system. The challenge of finding meteorites varies enormously depending on the environment. In most landscapes, meteorites are needles in haystacks, small dark rocks hidden among countless terrestrial stones. But certain environments concentrate meteorites or make them easier to spot, and these have become the focus of systematic recovery efforts. Antarctica has proven to be the most productive hunting ground for meteorites, yielding tens of thousands of specimens since systematic searches began in the 1970s. The continent's unique conditions create a natural meteorite concentration mechanism. Meteorites that fall on the Antarctic ice sheet become buried by subsequent snowfall and are carried by the slow flow of glaciers toward the coast. When glaciers encounter obstacles such as mountain ranges, the ice is forced upward and ablates away, leaving behind the meteorites it carried. These blue ice areas, where ancient ice is exposed at the surface, become natural collection zones for meteorites. A single blue ice field may contain meteorites that fell over hundreds of thousands of years, concentrated by the glacier's flow. The white ice and snow provide a stark contrast that makes dark meteorites easy to spot, and the cold, dry conditions preserve the meteorites with minimal weathering. The United States Antarctic Search for Meteorites program, known as ANSMET, has been conducting annual expeditions to Antarctica since 1976. Teams of scientists spend weeks camping on the ice, systematically searching blue ice areas on foot and by snowmobile. Each meteorite found is carefully documented, photographed, and collected using sterile techniques to prevent contamination. The specimens are then shipped to NASA's Johnson Space Center, where they are curated and made available to researchers worldwide. ANSMET and similar programs from Japan, China, and other nations have recovered over 60,000 meteorite specimens from Antarctica. This number far exceeds the total from all other sources combined, making Antarctica the dominant source of meteorites for scientific research. The Antarctic collection includes numerous rare types that would be unlikely to be found elsewhere, including many lunar and Martian meteorites. The success of Antarctic meteorite hunting has transformed the field of meteoritics. Before the Antarctic programs began, meteorite collections were limited and heavily biased toward iron meteorites and other distinctive types that were easily recognized. The Antarctic collections provide a much more representative sampling of the meteorite flux, including many small stony meteorites that would be overlooked in other environments. Hot deserts are the second most productive environment for meteorite recovery. Like Antarctica, deserts offer conditions that favor both preservation and discovery. The arid climate minimizes weathering, allowing meteorites to survive for thousands of years. The sparse vegetation and lack of soil cover make meteorites visible on the surface, and the light-colored sand or rock provides contrast that helps dark meteorites stand out. The Sahara Desert has yielded thousands of meteorites, many found by nomadic peoples who have learned to recognize these unusual stones. Meteorites from the Sahara enter the commercial market through dealers in Morocco and other North African countries. While the commercial trade raises concerns about scientific documentation and provenance, it has also made meteorites available to researchers and collectors who would otherwise have no access to such material. The deserts of Oman and other Arabian Peninsula countries have also proven productive. Systematic searches by international teams have recovered thousands of specimens, including many scientifically important finds. The Omani government has established regulations governing meteorite collection, attempting to balance scientific interests with commercial pressures. Australia's Nullarbor Plain is another significant source of meteorites. This vast flat limestone plain offers excellent conditions for meteorite preservation and recovery. The light-coloured surface makes dark meteorites visible from considerable distances, and the lack of vegetation allows systematic searching. Australian meteorite hunters have recovered numerous important specimens, including several lunar meteorites. The recovery of a witnessed fall, a meteorite that is collected shortly after being observed to fall, is a special event in meteoritics. Witnessed falls provide meteorites with known arrival dates and minimal terrestrial contamination. They also allow scientists to calculate the meteorite's pre-atmospheric orbit, providing information about where in the solar system the object originated. When a bright fireball is observed, networks of cameras and sensors can track its path and predict where any surviving fragments might have landed. Search teams can then be dispatched to the predicted fall zone, sometimes within hours of the event. The recovery of the Peekskill meteorite in 1992, the Chelyabinsk meteorites in 2013, and numerous other witnessed falls has been facilitated by such rapid response efforts. The search for meteorites from a witnessed fall is both exciting and challenging. The predicted fall zone may cover many square kilometres, and the fragments may be small and scattered. Searchers must cover the ground systematically, examining every unusual rock. The terrain may be difficult, the weather uncooperative, and the fragments elusive. Yet the reward of finding a freshly fallen meteorite, still bearing its pristine fusion crust, makes the effort worthwhile. Modern technology has enhanced meteorite hunting in several ways. GPS devices allow searchers to navigate precisely and record the locations of finds. Metal detectors can locate iron meteorites buried beneath the surface. Drones equipped with cameras can survey large areas quickly, identifying potential targets for ground investigation. And machine learning algorithms are being developed to identify meteorites in images, potentially automating the search process. The verification of a suspected meteorite requires careful analysis. Many rocks that appear unusual turn out to be terrestrial in origin, either natural formations or industrial slag. A true meteorite will typically have a fusion crust, the thin, glassy coating formed during atmospheric entry. It will often show regmaglypts, the thumbprint-like depressions created by ablation, and it will have a composition and structure distinct from terrestrial rocks. Laboratory analysis provides definitive identification. Meteorites contain minerals and textures not found in terrestrial rocks. Their isotopic compositions differ from Earth materials in characteristic ways. Iron meteorites display the Widmanstätten pattern when etched. Chondrites contain chondrules. These features, combined with chemical analysis, allow scientists to classify meteorites and determine their origins. The curation of meteorites is essential for their long-term scientific value. Proper storage prevents contamination and weathering that could compromise future analyses. Documentation of find locations, circumstances, and any associated observations preserves information that might otherwise be lost. And making specimens available to researchers ensures that meteorites contribute to scientific knowledge rather than sitting forgotten in private collections. Major meteorite collections are maintained by museums and research institutions around the world. The Smithsonian Institution's National Museum of Natural History holds one of the largest collections, with over 600,000 specimens. The Natural History Museum in London, the American Museum of Natural History in New York, and numerous other institutions maintain significant collections. These repositories serve as libraries of cosmic material, available to qualified researchers for study. The commercial trade in meteorites is a controversial aspect of the field. On one hand, commercial hunters have recovered many important specimens that might otherwise have been lost. The financial incentive motivates searches in remote areas and ensures that meteorites are recognized and preserved. On the other hand, commercial pressures can lead to inadequate documentation, destruction of scientific context, and concentration of specimens in private hands where they are unavailable for research. Different countries have different laws governing meteorite ownership and export. In some nations, meteorites are considered national patrimony and cannot be legally exported. In others, they belong to the landowner on whose property they fall. The legal landscape is complex and varies widely, creating challenges for both commercial dealers and scientific researchers. For amateur enthusiasts, meteorite hunting offers a unique connection to the cosmos. The possibility of finding a piece of another world, of holding something that travelled millions of miles through space, is a powerful motivation. Many amateur hunters have made significant discoveries, contributing to scientific knowledge while pursuing their passion. The experience of finding a meteorite is difficult to describe to those who have not experienced it. There is the initial moment of recognition, when an unusual rock catches your eye and you realize it might be something special. There is the careful examination, looking for the telltale signs of extraterrestrial origin. And there is the confirmation, when analysis reveals that you have indeed found a visitor from space. Whether conducted by professional scientists in Antarctica or amateur enthusiasts in local fields, meteorite hunting connects us to the broader universe. Each recovered specimen is a data point, a sample of material that can teach us about the solar system's history and composition. And each find is a small miracle, a piece of cosmic debris that happened to land where someone would notice it, pick it up, and recognize it for what it is. Chapter 11. Meteors and Life on Earth, Extinction and Creation. The relationship between meteors and life on Earth is one of profound paradox. The same cosmic bombardment that has repeatedly devastated our planet's biosphere may also have been essential for life's emergence and evolution. Impacts have caused mass extinctions, wiping out dominant life forms and reshaping the course of biological history. Yet impacts may also have delivered water and organic compounds to the early Earth, providing the raw materials from which life arose. Understanding this dual role of meteors as both destroyers and creators illuminates the deep connections between Earth and the cosmos. The most famous example of impact-driven extinction is the event that ended the age of dinosaurs 66 million years ago. The Chicxulub impact, caused by an asteroid approximately 10 to 15 kilometers in diameter, triggered a global catastrophe that eliminated approximately 75% of all species on Earth. The non-avian dinosaurs, which had dominated terrestrial ecosystems for over 150 million years, vanished entirely. Marine reptiles, flying pterosaurs and ammonites also disappeared. The world that emerged from the aftermath was fundamentally different from the one that had existed before. The evidence for the impact origin of this extinction has become overwhelming since the hypothesis was first proposed in 1980. The iridium anomaly at the geological boundary, the discovery of the Chicxulub crater, the presence of shocked quartz and impact spherules in boundary sediments, and the precise timing of the extinction all point to a cosmic cause. While some scientists have argued that volcanic activity, particularly the massive eruptions that created the Deccan Traps in India, contributed to the extinction, the impact remains the primary trigger. The mechanisms by which the Chicxulub impact caused extinction were multiple and devastating. The immediate effects included a blast wave that devastated everything within hundreds of kilometers, tsunamis that swept across the Gulf of Mexico and beyond, and wildfires ignited by the thermal radiation from the impact fireball and the re-entry of hot ejecta. These immediate effects would have killed countless organisms in the impact region and surrounding areas. The longer-term effects were even more consequential. The impact ejected vast quantities of dust and aerosols into the atmosphere, blocking sunlight and causing global temperatures to plummet. The darkness may have persisted for months or years, causing the collapse of photosynthesis and the food chains that depended on it. Sulfur, released from the target rocks, combined with water to form sulfuric acid, which fell as acid rain, devastating both terrestrial and marine ecosystems. The recovery from the Chicxulub impact took millions of years. The immediate aftermath was a world of darkness, cold, and acid rain, hostile to most forms of life. Gradually, conditions improved, and survivors began to diversify and fill the ecological niches left vacant by the extinction. Among the survivors were small mammals, which had lived in the shadow of the dinosaurs for over 100 million years. With the dinosaurs gone, mammals underwent a rapid evolutionary radiation, eventually giving rise to the diverse forms we see today, including ourselves. The Chicxulub extinction is the best documented example of impact-driven biological catastrophe, but it may not be unique. Scientists have searched for impact signatures at other extinction boundaries with varying degrees of success. The end Permian extinction, the largest in Earth's history, has been linked by some researchers to impact events, though the evidence remains controversial. Other extinctions have also been proposed to have impact connections, though none as firmly established as the end Cretaceous event. The recognition that impacts can cause mass extinctions has transformed our understanding of biological history. Before the Alvarez hypothesis, extinctions were generally attributed to gradual environmental changes, such as climate shifts or sea level fluctuations. The idea that a single catastrophic event could reshape the biosphere in an instant was revolutionary. It introduced an element of contingency into evolutionary history, suggesting that the course of life on Earth has been shaped not only by gradual adaptation, but also by sudden, unpredictable catastrophes. This recognition has implications for our own future. If impacts have caused mass extinctions in the past, they could do so again. The Chelyabinsk event of 2013 demonstrated that even relatively small objects can cause significant damage. Larger objects, capable of regional or global devastation, exist in the near-Earth population. The development of planetary defense capabilities, including systems to detect and deflect threatening objects, has become a priority for space agencies around the world. Yet the relationship between impacts and life is not solely destructive. There is growing evidence that impacts may have played positive roles in the emergence and evolution of life on Earth. The delivery of water and organic compounds by meteorites and comets may have been essential for creating the conditions in which life could arise. The early Earth, during the first few 100 million years after its formation, was a very different world from the one we know today. The planet was hot, volcanic, and bombarded by debris left over from the formation of the solar system. The atmosphere was likely composed of carbon dioxide, nitrogen, and water vapor, with little or no free oxygen. The oceans, if they existed, may have been repeatedly vaporized by large impacts. During this period, known as the Hadean Eon, the delivery of material from space may have been crucial for establishing the conditions for life. Comets and water-rich asteroids may have delivered much of Earth's water, filling the oceans that would become the cradle of life. Carbonaceous meteorites may have delivered organic compounds, including amino acids and nuclear bases, providing the building blocks from which life would eventually emerge. The idea that life's ingredients came from space is not new, but it has gained support from the analysis of meteorites and comets. The Murchison meteorite, as we discussed earlier, contains over 90 different amino acids, demonstrating that these essential molecules can form in space without biological involvement. Other meteorites contain nuclear bases, sugars, and other organic compounds relevant to biochemistry. And observations of comets have revealed the presence of complex organic molecules in their compositions. The delivery of organic compounds by meteorites would have been particularly important during the late heavy bombardment, the period of intense impact activity that occurred approximately 3.8 to 4.1 billion years ago. During this time, the inner solar system was subjected to a barrage of asteroids and comets, possibly triggered by gravitational disturbances from the giant planets. While large impacts would have been devastating, smaller impacts would have continuously delivered organic material to Earth's surface. Some researchers have proposed that impacts may have done more than deliver raw materials. The energy released by impacts could have driven chemical reactions that synthesized more complex molecules from simpler precursors. Impact craters may have created sheltered environments where organic chemistry could proceed, protected from the harsh conditions of the early Earth. And the heat from impacts may have created hydrothermal systems similar to those found at mid-ocean ridges today, environments that some scientists believe may have been the birthplace of life. The hypothesis that life originated in impact-related environments remains speculative, but it illustrates the complex relationship between cosmic bombardment and biology. Impacts are not simply destructive events, but can also be creative, generating new conditions and opportunities. The same processes that cause mass extinctions can also open ecological niches for new forms of life to evolve and diversify. The evolutionary consequences of impacts extend beyond mass extinctions. Even smaller impacts, those that do not cause global catastrophes, can have significant biological effects. Regional devastation can eliminate local populations, creating opportunities for migration and speciation. The environmental changes triggered by impacts can alter selection pressures, favouring some traits over others. And the psychological impact of witnessing a major impact event, if humans were present, could have cultural and behavioural consequences. The fossil record preserves evidence of life's response to impacts over billions of years. The patterns of extinction and recovery, the timing of evolutionary innovations, and the distribution of species across continents all bear the imprint of cosmic events. Reading this record requires integrating geological, paleontological, and astronomical data, a multidisciplinary effort that continues to yield new insights. Looking forward, the relationship between impacts and life will continue to evolve. As humanity develops the capability to detect and deflect threatening objects, we may be able to prevent future impact catastrophes. This would represent a profound change in the relationship between Earth and the cosmos, the first time in 4.5 billion years that a species on this planet has been able to protect itself from cosmic bombardments. Yet even as we develop these capabilities, we should remember the positive roles that impacts have played in Earth's history. The water we drink, the organic molecules in our bodies, and the evolutionary history that produced us may all owe something to the cosmic visitors that have been arriving on Earth since its formation. Meteors are not simply threats to be defended against, but messengers from a universe that has shaped our world in ways both destructive and creative. Chapter 12. The Future of Meteor Science and Planetary Defense. As we look toward the future, the study of meteors stands at an exciting crossroads. New technologies are revolutionizing our ability to observe, track, and analyze these cosmic visitors. International cooperation is expanding the scope of meteor research and planetary defense efforts, and ambitious missions are being planned to visit asteroids and comets, returning samples that will deepen our understanding of the solar system's small bodies. The coming decades promise discoveries that we cannot yet imagine, building on the foundation of knowledge that generations of scientists have constructed. The detection and tracking of near-Earth objects has become a global priority. Networks of telescopes continuously scan the sky, searching for asteroids and comets that might pose a threat to Earth. The goal is to discover potentially hazardous objects years or decades before any possible impact, providing time to assess the threat and, if necessary, take action to prevent a catastrophe. This effort represents humanity's first systematic attempt to protect itself from cosmic bombardment, a capability that no species on Earth has ever possessed before. NASA established the Planetary Defense Coordination Office in 2016 to organize and lead American efforts in this area. The office coordinates the detection and tracking of potentially hazardous objects, defined as those whose orbits bring them within 5 million miles of Earth's orbit and whose size is large enough to cause significant damage, generally 30 to 50 meters or larger. The office also studies strategies and technologies for mitigating potential impacts and issues warnings about possible effects of predicted close approaches or impacts. The foundation of planetary defense is discovery. Astronomers have urged that the first step in protecting Earth from future impacts must be to learn what potential impactors are out there. You cannot deflect an asteroid you do not know exists. The surveys currently in operation have discovered the vast majority of near-Earth asteroids larger than 1 kilometre in diameter, the size threshold above which an impact could cause global catastrophe. But many smaller objects remain undiscovered, including most of those in the 100 to 300 metre range that could devastate a region or trigger tsunamis if they struck the ocean. The Vera C. Rubin Observatory, currently under construction in Chile, will dramatically accelerate the discovery of near-Earth objects when it begins operations. This facility, with its 8.4-metre mirror and 3.2 gigapixel camera, will survey the entire visible sky every few nights, detecting objects far fainter than current surveys can reach. Over its 10-year primary mission, the Rubin Observatory is expected to increase the known population of near-Earth objects by a factor of 10 or more, providing a much more complete picture of the cosmic environment through which Earth travels. Space-based telescopes offer advantages over ground-based facilities for certain aspects of near-Earth object detection. A telescope in orbit around the Sun, positioned interior to Earth's orbit, could detect objects approaching from the sunward direction, a blind spot for ground-based observers. NASA's ENEO Surveyor mission, planned for launch in the coming years, will operate from such a vantage point, using infrared sensors to detect the heat emitted by asteroids, regardless of how much sunlight they reflect. The characterization of discovered objects is as important as their detection. Knowing that an asteroid exists is not enough. We must also understand its size, shape, composition, rotation rate, and orbital parameters to assess the threat it poses and to plan any deflection mission. Ground-based radar observations can provide detailed information about nearby asteroids, revealing their shapes and surface features with resolution comparable to spacecraft imagery. Spectroscopic observations reveal composition, helping scientists understand what an asteroid is made of and how it might respond to deflection attempts. The Double Asteroid Redirection Test, known as DART, represented a historic milestone in planetary defense. Launched in November 2021, DART was designed to test whether a spacecraft impact could change the orbit of an asteroid. The target was Dimorphos, a small moon orbiting the larger asteroid Didymos. Neither asteroid posed any threat to Earth. They were chosen specifically because the binary system allowed precise measurement of any orbital change. On September 26, 2022, DART successfully impacted Dimorphos at a velocity of approximately 6.6 kilometers per second. The impact was observed by telescopes around the world and by a small Italian CubeSat that had separated from DART shortly before the collision. The results exceeded expectations. The impact shortened Dimorphos's orbital period around Didymos by approximately 32 minutes, far more than the minimum success threshold of 73 seconds. This demonstrated that kinetic impactor technology is a viable method for deflecting asteroids. The success of DART has profound implications for planetary defense. For the first time, humanity has demonstrated the ability to intentionally change the orbit of a celestial body. While DART was a test conducted on a non-threatening target, the same technology could be applied to an asteroid on a collision course with Earth, provided the threat is discovered early enough. The key constraint is time. Deflecting an asteroid requires changing its velocity by only a small amount if the deflection is performed years or decades before the predicted impact. The same deflection becomes much more difficult or impossible if attempted only months or weeks in advance. The European Space Agency's HERA mission, launched in 2024, will follow up on DART by conducting a detailed investigation of the Didymos system. HERA will measure the mass of Dimorphos, characterize the crater created by DART, and study the properties of both asteroids in detail. This information will help scientists understand exactly how the impact affected Dimorphos and will improve models used to predict the outcomes of future deflection attempts. Beyond kinetic impactors, scientists are studying other methods for deflecting threatening asteroids. The gravity tractor concept involves positioning a spacecraft near an asteroid and using the mutual gravitational attraction to slowly alter the asteroid's trajectory. This method is gentle and controllable, but requires years or decades to produce significant deflection. It might be used for fine-tuning after a kinetic impact, or for deflecting asteroids where impact is not feasible. Nuclear devices represent the most powerful option for asteroid deflection, capable of delivering far more energy than any kinetic impactor. A nuclear explosion near or on an asteroid's surface could vaporize material, creating a rocket-like thrust that pushes the asteroid onto a new trajectory. Alternatively, a sufficiently powerful explosion could fragment the asteroid entirely, though this approach carries risks if the fragments remain on collision courses. Nuclear deflection would likely be reserved for large asteroids or situations where limited warning time precludes gentler methods. Ion beam deflection is another concept under study. A spacecraft equipped with an ion engine would direct its exhaust plume at an asteroid's surface, slowly pushing the asteroid onto a new trajectory. Like the gravity tractor, this method is slow but controllable and could be used for precise adjustments. The technology for ion propulsion is well established, having been used on numerous deep space missions. The choice of deflection method would depend on the specific circumstances of the threat, the size and composition of the asteroid, the time available before impact, and the precision required. In practice, a combination of methods might be employed, with a kinetic impactor providing the initial deflection and a gravity tractor or ion beam system fine-tuning the trajectory to ensure the asteroid misses Earth by a safe margin. International cooperation is essential for effective planetary defense. Asteroids do not respect national boundaries, and an impact anywhere on Earth would have global consequences. The United Nations has established the International Asteroid Warning Network and the Space Mission Planning Advisory Group to coordinate international efforts in detection, characterization, and response planning. These bodies bring together space agencies, observatories, and research institutions from around the world to share data and develop coordinated response strategies. The legal and political frameworks for planetary defense are still evolving. Questions about who has the authority to decide on deflection attempts, who bears responsibility if a deflection fails or causes unintended consequences, and how the costs of planetary defense should be shared among nations remain largely unresolved. As the threat becomes better understood and deflection capabilities mature, these governance issues will require increasing attention. While planetary defense focuses on preventing impacts, meteor science more broadly continues to advance through new observational capabilities and analytical techniques. Networks of cameras and sensors monitor the sky continuously, recording meteors and calculating their trajectories with unprecedented precision. These observations reveal the structure of meteor showers, the orbits of sporadic meteoroids, and the flux of material entering Earth's atmosphere. The Global Meteor Network, a citizen science project, has deployed thousands of cameras operated by amateur astronomers around the world. These cameras record meteors automatically, and the data are combined to calculate orbits and identify shower associations. The network has already contributed to the discovery of new meteor showers and has provided valuable data on the structure of known showers. This democratization of meteor observation allows anyone with modest equipment to contribute to scientific research. Radar observations complement optical techniques, allowing meteors to be detected during daylight and through cloud cover. Advanced radar systems can measure not only the trajectories of meteors, but also their deceleration profiles, providing information about the density and structure of the meteoroids. Some radar systems can detect meteors too faint to be seen visually, extending observations to smaller particle sizes. Space-based observations offer perspectives impossible from the ground. Satellites have detected meteors entering Earth's atmosphere from above, providing data on the brightness and distribution of meteors across the entire planet. Future dedicated meteor observation satellites could provide continuous global coverage, detecting every significant meteor event regardless of weather or time of day. The analysis of meteorites continues to yield new discoveries as analytical techniques improve. Mass spectrometry can now measure isotopic ratios with precision sufficient to detect the signatures of individual stellar sources, revealing the nuclear processes that created the elements in meteorites. Electron microscopy can image structures at the atomic scale, revealing details of mineral formation and alteration. And synchrotron radiation facilities allow non-destructive analysis of meteorite interiors, preserving precious samples for future study. Sample return missions represent the ultimate in meteorite science, providing material collected under controlled conditions from known sources. NASA's OSIRIS-REx mission successfully returned samples from asteroid Bennu in September 2023, delivering approximately 250 grams of pristine asteroidal material to Earth. Initial analysis has revealed that Bennu's surface is rich in carbon and contains water-bearing minerals, confirming that such asteroids could have delivered water and organic compounds to the early Earth. Japan's Hayabusa 2 mission returned samples from asteroid Ryugu in December 2020, providing material from a different type of carbonaceous asteroid. The Ryugu samples have proven to be among the most primitive solar system material ever studied, containing organic compounds and pre-solar grains that predate the formation of the Sun. Comparison of the Bennu and Ryugu samples is revealing the diversity of carbonaceous asteroids and their potential contributions to Earth's volatile inventory. Future sample return missions are being planned to visit even more diverse targets. The Martian Moons Exploration mission, being developed by Japan, will return samples from Phobos, one of Mars's 2 small moons. These samples may contain material ejected from Mars by ancient impacts, providing Martian samples without the need to land on the planet's surface. Other proposed missions would return samples from comets, from metallic asteroids, and from main belt asteroids that have never been visited by spacecraft. The study of meteors and meteorites is increasingly integrated with other areas of planetary science. Understanding the small bodies of the solar system, the asteroids and comets from which meteors derive, requires combining data from telescopic observations, spacecraft missions, laboratory analysis of meteorites, and theoretical modelling. This multidisciplinary approach is revealing the complex histories of these objects and their roles in the formation and evolution of the solar system. Astrobiology, the study of life's origins and distribution in the universe, draws heavily on meteor science. The organic compounds in carbonaceous meteorites provide evidence that the building blocks of life can form in space. The delivery of these compounds to the early Earth by meteorites may have been essential for the emergence of life, and the possibility that meteorites could transfer life between planets, a hypothesis known as panspermia, remains an active area of research. The commercial development of space is beginning to intersect with meteor science and planetary defense. Companies are exploring the possibility of mining asteroids for valuable resources, including water, metals, and rare elements. While commercial asteroid mining remains in its early stages, the technologies being developed for resource extraction could also be applied to planetary defense. A spacecraft designed to extract material from an asteroid could potentially be adapted to deflect a threatening object. The growing presence of humanity in space also creates new vulnerabilities to meteor impacts. Spacecraft, space stations, and eventually lunar and Martian settlements will all be exposed to the flux of meteoroids that Earth's atmosphere currently protects us from. Understanding this flux and developing appropriate shielding and warning systems will be essential for the long-term human presence in space. As we contemplate the future of meteor science and planetary defense, we are reminded of how far we have come in just a few centuries. Our ancestors watched meteors with wonder and fear, interpreting them as omens or divine messages. Today, we understand their true nature, can predict their occurrence, and are developing the capability to protect ourselves from the largest and most dangerous. This transformation represents one of humanity's greatest intellectual achievements, a triumph of curiosity, observation, and reason over superstition and ignorance. Yet the wonder remains. No amount of scientific understanding can diminish the beauty of a meteor streaking across the night sky. No knowledge of orbital mechanics can make the sight of a fireball any less thrilling. The universe continues to send us these messengers, these fragments of ancient history wrapped in momentary fire, and we continue to watch with the same awe that our ancestors felt tens of thousands of years ago. The future will bring discoveries we cannot anticipate, technologies we cannot imagine, and perhaps challenges we are not yet prepared to face. But it will also bring continued wonder, continued curiosity, and continued connection to the cosmos that surrounds us. The story of meteors is far from over. In many ways, it is just beginning.